So as long as you stand behind this, then you're in field view.
Okay. So I can stand like over here.
Yeah, you could actually. You could stand anywhere from here to there. And when I introduce you, you'll move over to there and I'll stand here.
Sure. Sounds
So
good.
that we can both be in the field.
Can we lock that?
We can lock that door. What time do you have?
8:29.
Okay. That's a good idea. We should actually put a sign on the door, please use back door. Yeah. So, good morning, everyone, and for people online and people in the room here, welcome to our 2023 EET Symposium. And I'd like to introduce you Joao Fain, and he's going to present on his refrigerator temperature monitor. Go ahead.
Thanks, Mr. Brock. So let's get started here. As Mr. Brock said, my name is Joao Fain, and I will present you my senior project for the refrigerator temperature monitor. And Mr. Broad was my advisor during this project. So during this presentation, I'll go through a brief introduction, a functional overview of the project, the technical description, going through the kind of like a user manual, and the electronic description of the project, testing and results, and the conclusions that I got. So, in 2021, the culinary arts department had an issue with one of their refrigerators. One of their freezers failed during a weekend, and there was no one around to check on it. So they had a big financial loss because of that failure. And to avoid this kind of issues, they reached out to Mr. Broad with a project in mind to build a device that could monitor the temperature inside that refrigerator, and if something goes wrong again, it would sound an alarm, and anyone that could be passing by would hear it and avoid this kind of situations again. So for this project, they have three main requirements. The device must take 3 samples of temperature during the day. That's a health inspection requirement. And they have two different appliances that they must monitor. A freezer that should be kept between -22 and -18 degrees, and a fridge that goes from 1 to 4 degrees Celsius. So with that in mind, we got to this concept of the project. The device should have a display over here. That's an LCD that has 4 lines. The first one, I can show the real-time temperature, the temperature at that moment, and the other 3 I'm using to show the 3 samples that I'm taking during the day. There are some push buttons on the side of the display that are used for controlling the device, to select which is the appliance that the device will be installed at, or to adjust the clock. And when the temperature goes out of range, this buzzer over here will sound, an alarm will trigger, and that alarm can be silenced by pressing this push button. The device monitors the temperature by using this sensor that is installed inside the refrigerator. So I'll go through the functional overview of the project, how it was built, how does it work. This is an embedded circuit system, so it is all based on the microcontroller. So this here, the microcontroller over here, it basically dictates everything that my circuit will do, all the requirements for my circuit. For example, the voltage supply section over here of the block diagram. The power supply was selected to provide 5 volts to my circuit. Why? Because my microcontroller needs these 5 volts to function. I also added a charge pump that converts the 5 volts to -5, because some of the components that I have in my circuit, they need dual dual supply, both 5 and -5 volts. That's, for example, my temperature sensor. The temperature sensor that I'm using can read temperatures between -55 degrees to 150 degrees Celsius, and it outputs a voltage proportional to the temperature that is reading. And as it's reading negative temperatures, because I'm installing in a freezer, it needs a negative supply so it can give me a negative voltage also. And in order to feed that signal from the temperature sensor to my microcontroller, I needed to first treat the response from the sensor, because it will give me a negative output, and my microcontroller doesn't take negative inputs. So I needed to create an offset so I can get that signal to my microcontroller. And for that, I used the voltage divider to do an offset for that signal, and added the response from the temperature sensor with the voltage divider by using an operational amplifier. This is the section for the input signal, and for the microcontroller, it sends the temperature reading to the LCD. It also sets the warning signal, and it gets input from the user by using these push buttons here, the user interface with the push buttons. The microcontroller is based on a code to control all the circuit, and this code I have this flow chart here that shows how does my code works. So at the beginning of the program, I need to set the libraries, also set the input-output ports for the buzzer and the push buttons. Then I have to set also the display and the communication, because my LCD, it has to get messages from the MCU, and in order to get that data, I need to set the communication between my device and the LCD screen, and that's set by I2C. And also I need to configure the analog to digital converter and timer. And then here I enter the functionality part of the program. First, I select which appliance am I monitoring at that moment. Then the analog to digital converter starts getting the temperature reading, and then that temperature is then converted inside the digital signal that it gets is then converted inside the MCU to a temperature. That temperature is printed onto the LCD screen. Three samples of temperature during the day are kept on my device, and then the temperature reading is then compared with the determined range. If the temperature is out of range, then the buzzer will trigger, and it can be silenced by pressing a push button and start all over again. If it's not out of range, if the refrigerator is functioning properly, it just goes back to the reading of the temperature again. Now I'll go to the technical description. First, I'll show you my device, go through a brief user manual, like let's say, how does the device work, and then I'll go through the electronical description. So here is the final device. When it turns on, we'll show a message here. Then on the first line, it will display which appliance it is selected to work on, and it starts reading the temperature. The first line here, you'll see the current time and temperature that it's reading, and the second, third, and fourth line, you'll show the samples that it's keeping through the day. The 3 samples are kept for 24 hours, and then they are overreading. This device is set to get a sample at midnight, at 8 a.m. and at 4 p.m. So at midnight it takes a reading. Next day, midnight again, it will overwrite this reading over here. The sensor goes out from the side of the device, and here it will go to inside the refrigerator. These buttons are used for selecting the mode of operation and setting the clock. By pressing enter, you can select which appliance that you want to monitor. Up and down, you select between freezer and fridge. Enter to confirm. And to set the clock, press up and down push buttons together. Then a message will show up asking you to adjust the clock. You use up and down to get to the right time, press enter to confirm. And here's the buzzer. Whenever the temperature goes out of range, this buzzer will sound an alarm. That can be sounded by pressing the push button. Or if the temperature goes back inside of the range normally, the buzzer would shut also. If you press the silence to kill the alarm, it will only sound again if the temperature goes back inside of range and out again, because you don't want to be all the time pressing the silence push button to shut the alarm. It would be quite annoying. So now we'll go to the electronic description. This is the schematic of my device. This is the whole circuit. I'll go through every part of this schematic separately here to make it easier to see. So first is the voltage converter. This component is necessary because I need both positive and negative input, voltage input to my device. So here it is fed 5 volts from the power supply, and it outputs -5 volts. The component that I use to do that is the LMC 7660 from Texas Instruments, and it also needs 2 decoupling capacitors connected here. They are used just to keep a more steady output that don't oscillate much, because too much oscillation could interfere with my signal, could not give me a good signal, good output. Then I have the temperature sensor that is right here. As the temperature sensor must be outside of the board, must be inside of the refrigerator, it is connected to my circuit with an external, with a connector, with a pin header. This sensor gets 5 volts from the power supply. It's connected to ground, and this pin 2 over here is where I get the output from the sensor. In order for me to get a negative reading, a negative temperature, I have to connect a resistor between the output pin to the negative supply of 5 volts. The temperature sensor that I used for this project was the LM35. Like I said, it ranges from minus 55 degrees Celsius to 150 and has a conversion of a factor of 100 for the conversion. It gives me a voltage of 0.1 for 10 degrees. So after this, I need the input signal circuit. As I told you before, my microcontroller, it only gets a positive reading. It cannot give an input of a negative voltage. So I need to treat the signal from the LM35. For that, I use the summer op-amp over here, the LF411. That would add the voltage that I get from my sensor with an offset that comes from this voltage divider over here. I connected these resistors R9 and R11 to set the gain for the LF411. I try to minimize the gain, so I have a signal again closer to 1, because I didn't want to complicate my life when I'm treating the voltage that I get from the LM35. I try to get as close as 1 as possible, so I can have an easier way to convert the voltage to temperature back again in my microcontroller. Here on pin 6 of this LF401, of this op-amp, I have the output voltage. This output voltage would be inputted to my microcontroller. And this device also needs negative and positive inputs for it to function the way that I need it to. So that's another reason I needed the voltage converter circuitry that I applied to the circuit. So next, I have the real-time clock. So as one of the requirements for this project was to keep three temperature signal, keep 3 temperature readings at certain times of the day, I needed a way to keep track of time accurately. So I used a real-time clock. It's the S1307, the circuit the component that I selected. It has a crystal oscillator connected to its pins 1 and 2, a battery connected to pin 3. This external battery is used to maintain the time even if my device is not plugged into the outlet, so you don't have to set the clock every time there's a power failure. And here, the pins 5 and 6 for the RTC module here are where the connection between this component and my MCU happens. It also connects to my microcontroller via I2C. There's a mean of communication. It gets a signal. It gets like a message to tell that the microcontroller is ready for getting information from it, or it gets a signal that says that the microcontroller is sending information to that device. So whenever I need to get time from this component, my microcontroller will send some data, and the real-time clock will know it's ready for information and send the time for my microcontroller so I can print it to the LCD. Next is the LCD connection. Here would be the LCD. The pins 1 and 2 over here are responsible for the backlight of the LCD. Pins 3 and 4 are the supply. 5 and 6, as I explained for the RTC, are the same thing. They are responsible for the connection. So whenever I'm writing to the LCD, I'm sending the temperature to the LCD. I'll send a message to the serial data pin over here, telling them they must be ready for receiving information because I need to send you a temperature reading. Pin 7 is the pin 7 is responsible for the brightness of the text that goes into the LCD. So by adjusting this potentiometer over here, I can adjust how bright is the text that goes into the screen. So we can adjust the visibility of the LCD. These two resistors, R3 and R4, are connected to the lines of the I2C communication. Those are required to kind of power up the line to make the communication feasible. And the last part of the schematic is the microcontroller. This is the microcontroller that I'm using, the Mega 328B. Everything is connected to this part. This is the core of the circuit. The ADC, the voltage that comes from the temperature sensor, is inputted on this pin over here. These are the pins that are connected to both the LCD and the RTC, depending on what kind of message do I need, or if I have to set the clock, or if I have to send the temperature. It's all done by these two pins over here, 27 and 28. Pin 6 is a hardware selection of the device the appliance that we would monitor. So I have a jumper connected over here to pin 6, and the middle pin of the jumper, pin 2, it is connected to my circuit. If I needed to monitor the fridge as the default setting of my device, I connect this pin to 5 volts. I use a cap to connect this pin to 5 volts, and it will default the device to a fridge. If I need to connect it to a freezer, I can change this cap here to connect the pin to ground, and it will default my device to a freezer. Pins 10 to 14 are the input-output pins. They interact with the user. Pin 10 is the warning buzzer, the warning signal. Pins 11 through 14 are the push buttons, the enter, up, down, and silence. And here on this side, I have the ICSP connector. This is if I need to change something in the code for my device. Is there any bug that is I have problem with any functionality here that I want to change, or maybe the temperature range is not right. The temperature range is not -22 to -18 anymore. I have to change that. So I would change by connecting an ICSP over here that will reprogram the microcontroller. So this is how my device works. And after that, I went to the testing of the device that I got, testing and results. So there are two main functionalities of this device. I have to accurately measure the temperature, and I have to give a warning signal that can be audible for someone that is going around. So those are the two tests that I selected to do. First, I'll discuss the accuracy of the temperature. This test was done at 3 different situations. First, at a temperature below 0, the second at room temperature, and the other one at a higher temperature, about 50 to 60 degrees. Those tests were done, each one in 5 trials. And the results that you'll see will be the average of each of the situations. So here, I done the test comparing the temperature that my device gave with a thermometer that I got from our lab. And those were the results that I got. As you can see here, the temperature was tracking very closely to one another. These are the average that I got, for example, low temperature, minus 2.66 for the device that I built. For the thermometer, I got minus 2.68. The average between the 5 trials was of 3.99% of error between them. So the average of all the trials was, the error from all the trials was 1.55%. So it was a very low error. It was a very low difference between the temperature that my device gave and the thermometer was giving me. So I can say that this device can track the temperature very accurately. So it was, at least this part of the functionality of the device was met. It will be good. The next was the audibility level of the warning signal. For that, I tested the two possible violations. For a lower temperature breach, when the temperature goes under the lower limit, or an upper level breach, when the temperature goes above the upper limit of the range that it should be. The warning signal was triggered for both of the situations, and using a sound level meter, I measured the dB level that the warning, the buzzer was giving me. WorkSafe New Brunswick states that a sound above 85 dBs for a long, for an extended exposure could be harmful for the user. So what did I do? My goal was to reach above this 85 dBs threshold. Why? If it's harmful. It's not harmful if I do it for a very short period, because the warning signal must be heard and then quickly you have to go there and silence it and discover what is going on with the refrigerator. So it should not be there for long, but must be high enough so someone can hear it. So these were the results that I got from this test. For a lower limit violation, I had a little bit louder signal compared to the upper limit violation, but all of the measurements were above the threshold that I desired. So the warning signal must be at a good level, so someone that's passing by will hear it and go check what's going on with the device. So it was also another feature that the device was able to achieve. And I'll go to my conclusions right now. So the device that I built was fully functional. It is capable of selecting the appliance between freezer and fridge, as it was a requirement from the stakeholder. It accurately measures the temperature with an average error of 1.55%. So the temperature that the device gives, it's very close to what is real. It registered 3 samples a day, as it's a requirement from the health inspection. I can't get these three sample temperatures. It makes life easier for people working over there. Don't have to write them down manually. The device does that for them. And it provides a warning signal for an undesirable condition. And this project is a part 1 of 2. The main goal, the first thought of the project was to build a device that could send a text message or an email or something to warn them, to warn the stakeholders about a failure. So this part will be done in the subsequent part of this project. The first part was I already built the device I already built a foundation to that. There's a device that can monitor the temperature accurately, that already sends a signal or already checks if there's some failure going on, and that I achieved. So the part of the communication will be done possibly next year. Okay, these are my references. And I'd like to thank you. Thanks, Mr. Broad, for all the advising during the project. Thanks to Chef Brinson for giving me the opportunity to work on this project with them. I hope you guys liked it. Thank you. So, sorry.
Yeah, go ahead.
So, here's the device. I'll power it up. Let's go to the demonstration. So right now it's tracking the temperature at about 25 degrees, 23. It takes a little bit of time to adjust it because it gets a measurement, an average of some values of some readings. So when we power it up, it takes a time to register those readings, and then will give us the correct average. So it's tracking about 23.7 degrees. Right now it's set for monitor room temperature, just so we don't have the buzzer going all the time, like that. And I brought something here to trigger the alarm. So now the buzzer is sounding because it's outside of the range. It's measuring at 43 degrees. If I press the silence button, it's because my temperature is set for 35, so if it goes outside back, it would sound again. But that is the device. I also have like an ice gel here, so I can get the temperature lower. So it will sound now that is below 15 degrees. Press it, it sounds the alarm. The response is a little bit slower than, for example, a thermocouple because of the nature of the temperature sensor here. But yeah, that is it.
Any questions? Mr. Fate?
Decided the mode, the demonstrate the mode.
Oh yeah.
Can you, maybe that's the first question. Can you show us the modes?
Press enter here. We'll ask for selecting the appliance, but press down. I can choose between the two of them and enter to confirm. If I want to change the clock, press these two together.
And can you explain, I have two questions about the, I guess, since we're still here, before we go over to your slides, we'll ask about this, the demonstration that you showed here. You had mentioned that the there was a hardware selection
Yes.
for refrigerator or freezer,
Mhm.
and then you're showing a software selection as well. Can you explain those? Why do you have the two? And
The hardware selection is because the device will be installed in one of the appliances that they desire. So it must keep the selection must keep can I say, it must remember the selection that it has. It must remember which appliance it is monitoring for, in case of a power failure. If in case if the power goes down, it goes back up, it should always be selecting that. It should always be monitoring that device. That's why there's a hardware selection. The software, it was something that we previously discussed with the stakeholders, that we needed to select which kind of appliance we need, or which kind of appliance we are monitoring. So I added this feature to choose in between the two of them, but the software selection is not, how can I say, is not remembered by the device. Once the power goes down, if you change the selection, it will always go back to the default. It will always go back to where the jumper is connected.
so is it more of a troubleshooting tool, or
Yeah, maybe just to make a test with the device on another appliance, but if you want to permanently install that in another refrigerator, you have to do the hardware selection, change the position of the jumper.
Okay, can you also explain while we're still here? I see a real-time temperature reading that's happening.
Yes.
The clock's updating every second and you see the real-time temperature. Where will the historical readings display?
They will display right here, these two lines over here. They're not shown because when the power goes down, those readings will be lost. They are kept only while we have power on the device. So once we get to the next one, will be at 4 p.m. So we have to wait a little bit.
Yeah.
It will go over here, midnight here, and 8 a.m. over here.
Would you be able to take some time, could you just maybe set the clock to 3:59 or something and then let it show us how it's going to log that 4 p.m. reading? Or any of them, whichever one you want.
In a minute, we'll.
And maybe while this is happening, maybe there's another question that could be asked during this time. Anybody have another question?
Well, we have to return to this slide.
Yeah. Well, that's okay. We can go to the slides and it's pretty easy to switch back and forth. So maybe at the end you can bring back the visual of the project.
One thing I noticed when you were showing your testing, your first diagram for your first test, how do you differentiate the three?
You mean for the temperature?
Yeah, what's the difference between the three?
It's basically what temperature am I evaluating? Because at run 1 is at negative temperatures, below 0 degrees. At run 2 is room temperature, and run 3 was above 40 degrees.
Right. It should have been clearly identified here, though. Just makes it a little easier on us.
While we're here, I guess, on the next slide, where you've shown your accuracy results, your low temperature is still considerably above what your freezer temperatures would be. What influenced your decision to use these numbers in your test?
I didn't have access to the freezer during the testings. I did the test mostly at home. So this was what I used, the same gel bag. So that's why I couldn't get to the minus 20 degrees Celsius to test that.
how about the, let's visit slides 22 and 23. So
Yes.
22 first.
Yes.
And then, so you did this audibility level test on the warning signal. Maybe go to slide 23. How can you explain with the same buzzer why you got two different
I can't.
ratings for one for
Honestly-
high temp over temperature and one for under temperature?
Honestly, I cannot explain.
Okay.
I don't know if some variation of the voltage that the device was giving would interfere in the audibility level or something, because I really cannot explain. It was the same thing,
Yeah.
same distance and everything. So
Because based on your testing procedure,
yes.
you weren't actually changing the temperature of the buzzer.
No.
So you would expect that the buzzer still operating under the same conditions would give you the same output. But,
Yeah.
so that's curious.
Yeah, the measurements we're taking, I did, it was like 30 seconds for the warning signal, and then I silenced, waited till the temperature go back in, made it go back out again, but always the same temperature that was going on, and I don't know why that happened. There was a difference between the two of them. They were all above the threshold that I desired, but there is a difference between the lower and the upper limit, and I cannot explain that why.
Okay. Anybody else have any questions?
Just
yeah,
one
you
second. There's the register at 4 p.m.
Okay, so 4 p.m. goes on row 4,
Yes.
and so they'll always be stored in the same
row,
position,
yeah,
like
same position.
midnight would be in
The
row
first, yeah,
2,
the second, exactly.
and 8 a.m. in row 3.
Yeah.
Okay.
Is there
I
a
selected those times just to be 8 hours apart. I have to take 3 samples. The day has 24 hours. I divided it in 8, but there is no specific reason why it's midnight, 8, and 4. It just needs
It's
to
just
be-
that the stakeholder required 3 readings
Three
per
readings,
24-hour
yeah.
period, so that makes sense.
It doesn't
Yeah.
really matter what time the readings are taken.
Yeah.
I was gonna say, is there a reason you chose not to store those historical values in long-term storage? Something that would survive through a restart?
Didn't know how to actually.
The Mega 320p is steep ROM, I believe.
But once you keep writing to that, I know that it has like a limit.
Yeah.
So that's why I didn't want to deal with that, and thought that it could give an issue for the programmer later. But the next phase of the communication, what we thought was these samples could be sent once a day to the stakeholder once we have that feature installed to the device. So for now, I really didn't know how to do that.
For the amount of time that there's a power outage in this building, I don't know how many power outages we get per year here, but
Infrequent.
it's very infrequent, so perhaps, I don't know, maybe the stakeholder was okay with that, maybe they weren't, I don't know, but I would think that would be a very minor thing to have them, if once a year, you know, the readings disappeared from the screen and then within 8 hours they start coming back, it's
And
probably not a big deal.
As we don't have to keep the reading like on those exact times, you can, if there's a power outage, I lose these readings here, we can during the day take 3 other readings, and there's no harm in that.
What happens to the real-time clock if there's a power outage?
It goes back at the same time.
It retains its time,
Yeah.
so it's,
16:05.
yeah.
Just a moment. 16:05.
Okay. So is, I don't recall in the schematic, is there a battery backup? Or
Yeah, it does.
there's a battery in the circuit?
Yes.
Maybe you could show us that?
Uh,
This is something the stakeholders want to know about, right?
Right here on pin 3.
Oh, there it is, yeah, right, okay. So what's the procedure for changing that battery? Because the stakeholder here, they might want to know, right?
The battery can be, you have to open it over the, you have to open the device here. There's like those lithium batteries. Just remove it and put another one in.
So it's
Very easy to assess.
a coin cell battery?
Yeah.
Okay.
Yeah. But the data sheet says the battery lasts for a very long time, like more than 10 years.
Under what condition?
I'm not entirely sure what is the exact condition, but
Because if I put a dead short on it, it's not going to last 10 years.
oh yeah, that's
Right?
last seconds.
Yeah.
Not even.
So how much, that's a good question then. How much does the RTC chip draw from the battery?
I don't know to answer that question.
Because that would, if it, just because the data sheet says that the battery would last 10 years, well, that might be, you mean the data sheet for the battery?
No, the data sheet for the RTC.
Oh, the RTC, yeah. So, okay.
Like while using it, it can last
Yeah.
a long time.
Any more questions? We have time for one more, maybe go to slide 14 then. What type of feedback is exhibited here or in regards to the LF411?
Sorry, feedback?
Yep. What type of feedback is this circuit imposing on the LF411?
Honestly, I didn't understand the question. Could you-
What type of feedback is used here in conjunction with the LF411?
It is connected as a summer op amp.
But that's an answer to a different question, right?
Yeah.
Yeah. Which resistors are responsible for the feedback?
The resistors are R9 and R11.
So it's R9. So if you follow R9 from the feedback is a signal that's returned from the output back to the input, right? So if you follow R9,
That'd be the positive feedback.
where does it connect?
It's connected to the negative.
Is it?
Negative to the
It's
negative.
marked with a negative sign. What do we call the
Yeah.
input?
Oh, okay.
They have names, right? The one that's marked with a positive symbol has this particular name on that op amp, right? And then the one that's marked with a negative terminal has a particular name. What are they called, do you know?
I don't remember the names. Positive and negative terminals are
They're called-
we usually call.
They're
positive
called
and
non-inverting and inverting, right?
Oh,
In op
yeah.
amps, right? Remember that?
Yeah, that's right.
So where does the R9 connect to?
R9 connects to the inverting.
Inverting.
Would be an inverting feedback?
So what type of feedback?
It's an inverting feedback?
They actually call it negative feedback,
Negative
right?
feedback.
Yeah.
Okay.
Yeah.
Yeah, I really don't remember that part.
I guess we're out of time now anyway, right? It's fine.
Yeah.
Like 15 minutes. Okay, thank you. Thank you. Thank you for attending today. Hope you yeah, that's gonna happen at some point. We're busy here for the next this week and then to the middle of next week, but we can set up something install it at your convenience after that. So say May 31st or later, whatever works for you. May 31st. Yeah. Maybe what I should do is make a percentage of the trade either on taking or on the for that, and that way you get credit for it. Great, Russ. Awesome. Thank you very much. See you around.
So I did take a look at this whole binder, like my final report.
Yeah.
Just wondering how we were supposed to submit
You don't submit the binder unless your advisor wants it.
Yeah.
Yeah, if he wants it, then you, but you need to submit into the Dropbox.
that. Yeah, I already did that, yeah. Just making sure, because I'm nervous, just a little ask for it. I didn't really get any information.
Just see him. I just give credit. Yep, thanks. I guess we could do one. Oh, sorry, I forget what to pronounce. Yeah, I guess so. Digital version. It's a lot to print out. 500 data. It's like a ream of paper for me. Just because there's so much things. It's really this is between 20 and 30. If your advisor needs it, then give them his time. Or if you want physical solutions for really, figured there's 6 instructors, so I'll do all the interviews today. Each day after that, let somebody else take a turn. We should definitely get one. Do you want me to do the whole thing? Maybe we should use the average one that Okay, so the next presentation, is there a question back here?
I think the live stream went down.
Did it go down?
The YouTube link.
It's possible. It says it's going, but I had a problem with the link, so I just streamed to a different link. But I don't have any of the contacts, so Dennis will have to deal with that when he comes. So the next presentation of the day is Mr. Jed Bakke, and he's going to present to you his solar seed dryer. Go ahead, Jed.
Hello, my dear classmates, colleagues, and dear instructors. Thank you for giving me this opportunity to present to you my project. So my project is solar seed dryer. So what I'll be discussing to you is the introduction about the solar seed dryer, its purpose, overview, block diagram, schematics, the testing and results, conclusions, including the recommendations and the cost and reference. So what is solar seed dryer? Solar seed dryer is a type of equipment designed to dry seeds using solar energy. A quick background about this is that solar seed dryer is very popular mostly in Asian countries. Also, even though it's popular in the Asian countries, it can be also used here in Canada. So why I choose this project? Back home in the Philippines during pandemic, we have this kind of, we cannot go out, so my father was like, love to plant. So what we have is that when we have spare or almost rotten fruits, the seeds on it are being dried through open sun drying. So what happened is during open sun drying, most of it is being blown away by the wind, getting by birds, animals, and it sometimes it's gonna be all blown away. So there's nothing left. So when during last term, during the proposal, that's why I proposed this project so that the seeds are being maintained. It is not being damaged through the winds and other animals. So what's the purpose of this project? The purpose of this project is to preserve the seeds, improve seed quality, extend storage life, cost effectiveness, energy efficiency, sustainability, and accessibility. So there are different kinds of solar seed dryer. First is the direct, indirect, mixed mode. For the direct solar seed dryer, it is just directly heated through the solar radiation. But in indirect solar dryer, there's a solar collector, and the drying chamber is isolated and the indirect solar dryer chamber, the chamber is isolated. So it's just the air from the going into the solar collector will go to the inside of the drying chamber. And for the mixed mode, it is a combination of the direct and the indirect solar dryer. So for my project, I choose the direct solar dryer. What does it features? It has a drying chamber, it has a ventilation system, control mechanism, and insulation. So for what I made for the drying chamber, I put a aluminum sheet where you can see it here. All of this is aluminum, and the aluminum tray which is also perforated. So for the ventilation system, I put a small hole here where air can come in, and it's fully sealed down here on the inside, so that when air comes in the drying chamber, it can help the heat inside the chamber to flow evenly in the seats. And here is I have a fan here, which acts as an exhaust, so that the heated air here will get out in the drying chamber, so that the moisture from the seeds gonna be released. So it helps in drying the seeds faster. So here is my concept drawing, where you can see the parts and that I use in building the project. So for the glass, I choose acrylic glass, since it's way cheaper and can still hold the heat inside without having a heat loss, without having too much heat loss. So my switch is located at the back of the solar the drying chamber, as you can see, and my temperature and humidity sensor is located inside the drying chamber. I put a small I put here a small piece of wood so that it can cover the sensors, because it is not really suitable for direct sunlight. So here is for the block diagram. So the flow of my project is that I have a wall adapter which is connected to the 120 volt AC source, and it is converted to the 12 volt DC, which will be supplied to the switch. So as my switch turn on, the switch indicator also illuminated. So from here, the 12 volt supply, it will go to the voltage regulator, which has an output of 5 volts. Why do I need two supply? Because for the 12 volts, it will supply only the fan, the relay, and for the 5 volts is to supply the other components in the circuit. So for the 5 volts, it supplies the temperature sensor, and the output of that temperature sensor goes to the voltage comparator together with the voltage divider. So this voltage comparator compares both the inputs of the voltage divider and from the temperature sensor. So once it overcome the voltage necessary to turn on the fan and to turn off the fan, it will show here that the fan will turn on, as well as the indicator will turn on also when the fan is on. So Here I use BJT switch for fast switching and a relay to turn on the relay quickly. And I have here a flyback diode, which when the 12 volts fan turns off, it can support, it can create a flow of current so that it will not damage the rest of the circuit. And also for the humidity sensor, same as the temperature sensor circuit, it also has a voltage divider going to the voltage converter. So what does it output is that it detects the level of relative humidity inside the chamber. So when the output is 20%, it will only blink one LED. So when it reaches 40, 60, and 80, the LED indicators are illuminated incrementally. So here are my major components. I use LMT84 for the temperature sensor, which has a temperature range of -50 to 150. And I use a humidity sensor of a brand of Honeywell, which is HIH4020, that has a 5 plus and minus 5% accuracy rate of detecting. So I use for my comparator, I use an op amp, which is an LM339 that has 4 outputs and a whole 12 volts DC fan. So here is my schematic diagram. So I will divide it for the 3 parts so that we can clearly understand. So first, the power supply circuit. So the 12 volts will flow and turn on the switch. So when, just like I said before, once it turns on, the LED here indicator will illuminate it. So from here, the current will flow to the voltage regulator and will make an output of 5 volts and 12 volts. And the 12 volts will just go through the relay and the fan. Next is the temperature sensor circuit. I use LMT84 since it is applicable for my circuit that I need the certain temperature, because before I use a LM741, but it doesn't work for me. I try another sensor to make it work. So here, the output of the temperature sensor is going to pin 6, which is the negative input of the comparator. And for my reference voltage, the output of the voltage divider is going to the pin 7, to the positive input of the comparator. So here, I use an inverting input so that once the output of the temperature is lower than the reference voltage, it will trigger and turn on the fan. That's the concept of this, because my sensor is linear, has a equivalent linear voltage. So the lower the voltage, the higher the temperature. So once it's once the temperature is and once the voltage is lower than the output of the temperature sensor, the output will be 0, which is the fan will not turn on. So for the next one, for the humidity sensor circuit, I use all the 4 output for the comparator, since I need 4 outputs for my LED. As you can see here, for the HRH 4022, same as the temperature sensor, it has also an equivalent. The humidity level has an equivalent voltage, so that I can compare both voltages, so that the output of it will turn on each LED indicators. So for here, I have here as you can see, I have here an 90K resistor. It's just because it is indicated in the data sheet that it needs to have a minimum load of 90K ohms, so that for the humidity sensor to work. So here, it's different from the temperature, since I'm using a non-inverting input, a non-inverting comparator, which means when the voltage output of the humidity sensor is higher than the reference voltages, it will turn on each LED here. So for here, once the humidity is above 20, the first LED indicator will turn on, and so on and so forth. I have here, as you can see, I have here the R16, R14, R20, and R18, which is pull-up resistors, because when the output signal is off, it will have something to where it can go, so it's not floating. So here we can see here the PCB design that I made to the progress of the project, where I find it difficult since it's my first time building a PCB. So my problem here before, it's not working because I didn't check the terminals and the footprints on it, which gave a problem in testing the circuit. So what I did is I removed the copper and connect some jumpers, and I connect jumpers to the right trace, and double check it with my schematic so that it will work. And then for And here is my actual PCB. So you can see, I use the terminal blocks for the fan, which is inside the drying chamber, also with the temperature sensor and humidity sensor. Then here we can see the finished project, the front and the back. So I put an insulation so that the heat will stay and reduce the heat loss, and it can also help for my seeds to easily dry. So for my testing with end results, my test one is the temperature sensor calibration, which the process is like just connect first the wall adapter to the source, switch on the dryer, and for my test equipment, I just use a blower to trigger the sensor and put it inside the drying chamber. So when I put it inside the drying chamber, I check the temperature for the thermometer and record the results. Also, I measure the output voltage from the sensor using DMF, because after I measuring the voltage of it, I check the data sheet from the sensor so that I can know what its equivalent voltage, equivalent temperature. So here is the transfer table for the LMT84. For the LMT84, as for the sensor, as you can see with the versus with the thermometer readings, it has the highest of 4 degrees Celsius difference, which is still acceptable. So for the formula, it is just the measured value, which is the T2 for the sensor and true value for the thermometer. And for the percent error is just the measured value minus true value over true value. So for my solar seed dryer, my my required temperature is for the seeds to dry is a minimum of 35 degrees Celsius and maximum of 60. That's the temperature that is allowable for the seeds to dry in a perfect condition without over drying the seeds. So for test 2, it's just a simple energy consumption test. I just use a water meter and just check if how much energy consumption I'll be getting, and just check for the solar radiation, the red screen, which will help me also determine the amount of energy for the month. So here is my test results. So we can conclude that the energy consumption is very low, since my power consumption is only 8 watts. So when the fan is on, I can just get a 13 milliamps current flow, and when it's off, it's 200. So it's really low that I don't need for my project. It's not necessary to have a solar panel. And for the conclusion and acknowledgement, I would like to thank my friends, my classmates, the instructor still here, for helping me throughout, even though it's really hard for me for to finish the project, but my results, my results was expected, so it's a good one. For the value of the project, for my previous memo, I assume that the estimated value of it is 600, and I only consume like 575, so I still save some money. For the future improvements, since the limitation for this is we can just only use this during summer or other days, as long as the temperature is above 30 to 35, we can use this project. For the future improvements, we can add some adjustable vents so that the air will not continuously come in when the temperature is really low, because it will just add up for the time of drying the seats. And we can use some digital sensors so that we can see actually and monitor the temperature readings and the humidity level that is needed for the seeds to be dry efficiently. So here's my reference. So that's it. So for my demonstration, so I don't know what you can see. see that I will first show you how that the fan will trigger using the hair blower. So since it's already above the set temperature, the fan already turned on. And for the humidity level, it shows that it's 20 degrees. The relative humidity is above 20 degrees and lower than 40. So it is really acceptable since it's already hot inside. The humidity level is only about 20. So I want to turn off the fan. And I'll just need to So it will just take a few minutes before the fan to turn off. I just don't have the eyes to lower it down. So I think that's it for my demonstration. It's just
Yeah, I got a question.
yeah.
Near the start of your PowerPoint slide, you had mentioned that you chose an acrylic glass for your project because it was way cheaper. Is that the best option?
It's not really the best option since it can cause over drying since it's really directly to the solar radiation from the sun. But it's just more efficient than the open sun drying because it's already sealed inside and insects cannot and the birds cannot just get it out from the chamber. So for me, it's for the best type of dryer is the indirect since it has a solar collector where when the solar collector heats up and air will just flow going to the inside of the drying chamber. For me, for the mix, it's not that efficient because it's not that efficient. It's just way more complex and costly since you're building both the
Sticking with your project,
yeah.
with the acrylic glass, does that impact any incoming solar radiation? Does it have any effect in that sense?
Yeah, it has an effect for my project, but it's not the acrylic glass is not that more efficient compared for the tempered. It's just cheaper so that it's still acceptable for my project. It's just the cost of the material.
Okay.
Why don't we go to the schematic?
bring us into the power supply section, please. That's great, thank you. How did you select the value for F1?
It's the one that's available on me, so that I won't buy another one. But
You're saying to me that if
That-
you had a 60 amp fuse available to me, to you, you're gonna
no,
stick it
it's,
in there?
it's way too big.
So how did you select the fuse?
It's just for my current is only 13, so that I should have only 1 or below 1 amp.
Ah.
But it's that.
So you're saying, are you saying that the fuse represented here is not the correct value?
Yeah,
It's incorrect.
yeah,
Okay, so what would be the correct value?
it's 1
And how would you determine that?
by or 500 below. Since the current on the circuit is the maximum is only 13 milliamps.
13 milliamps?
Yeah.
So what is the fuse protecting then?
It's not really that I can remove the fuse since it's really low.
No, but what's the fuse protecting? That was my question.
For the power supply,
The
it will
fuse
not,
is protecting the power supply?
so that it will not
What,
come back from the power supply with the circuit.
why do we use fuses? What's the fuse there to protect?
Protects the circuit of the
The circuit? Because, okay, so you're kind of bouncing around. First you said it's to
Yeah.
protect the power supply, now you're saying it's to protect the circuit. If it's to protect the power supply, well, what kind of power supply are you using?
just 12 volts
12 volt.
connected to the 120 AC source.
So it's 120
To
to 12 volt,
To 12.
120 AC to 12 volt DC power supply, wall mounted power supply, right? Is it regulated or unregulated?
It is fixed 5 volts. Based on the data sheets, it shows that it has a fixed 5 volts.
Regulated or
Yeah.
unregulated? Okay, so really, most of these power supplies are short circuit protected, and so the fuse isn't really to protect the power supply, is it? What's it there to protect?
Can you repeat the question?
The fuse isn't really there to protect the power supply, because most of these power supplies these days are short circuit protected anyway, in their design. So what's the fuse there to protect?
Not really that. I just
In your house, why do you have fuse, why do you have a circuit breaker panel, which at one time would have been a fuse panel? Why do we have circuit breakers and fuses?
it will protect for overcurrent.
To protect what?
Overcurrent.
You're not protecting
The-
overcurrent. What are you protecting from overcurrent? Why do you have these circuit breakers in your house? Let's use household example.
With a circuit breaker.
Yeah, why do we install circuit breakers in
So
a
that
house,
they-
for example? What's it there to protect?
So that to interrupt when short circuit, it will protect
Protect what? What will it protect?
it will not just protect the people, but the equipment that is connected into it. So it will just turn off when it.
What's conducting all this current that runs through the walls of my house, for example? What's conducting all this current? In my house, what's running through the walls that's conducting the current?
Yes,
The wiring, right?
yeah, the wires that.
So it's to protect
connected.
the circuit pathways, right? In your case, if it's a PCB, well, it'll keep the traces from burning off the board, okay? So the fuse will burn instead, okay? That's what it's there for. So, back to my question, what's an appropriate value of fuse here? You just said just chose one that I had available, but you didn't do any calculations to find out?
No, I really did.
Really, that's really important, right? Okay, maybe we spent enough time on that, but you rushed over here this regulator part of the circuit. You neglected to mention the purpose of C1, C2, and C3. Can you explain what those do, please?
The C1, C2, C3.
Yeah.
I use that for the it will filter with the excess current.
Excess current?
That it will not go back to the positive.
Okay. Anybody else have any questions?
Where does the 12 volts flow?
Well,
Yes.
Where does that 12 volts flow exactly?
to the fan. But it
Does it?
needs 12 volts to the fan.
Interesting.
Yeah, the 12 volts flows to the fan?
Yeah.
It does? Okay.
the-
How about on the next section of your schematic? I was hoping that you would have explained the purpose of D3.
Yeah, I told you that it's a flyback diode.
Okay, so explain how that diode does what it does.
So it will create a flow of current. When the relay turns off, it will make a big, like a inrush to the circuit, so it can store the charge, so it will not damage the rest of the circuit.
You're saying that D3 has the ability to store charge? So
I mean-
D3 is a capacitor?
No, I mean it can create the flow to the ground, to the excess.
So, okay, so let's say that K1 de-energizes. Okay? K1 de-energizes, we're talking about the K1 coil here, right?
Yeah.
K1 coil, put your pointer up on the K1 coil, okay? On the coil. So locate your pointer onto the coil there. I don't care if you use a laser pointer or if you use a mouse pointer, whatever it is, whatever works, okay? All right. Okay, so what happens to the coil? So point to the coil itself. Where's the coil? Right there, right? Okay, what happens at that coil when the magnetic field collapses?
It makes a sound, like a stuttering sounds.
Huh? No, what happens electrically?
It electrically it will
You want to go on to another question?
You mentioned that you choose a different sensor because the first one didn't work. Why didn't it work?
I think it didn't work because I used to have. I just don't know really how it works for that sensor, and for here, I just searched some through the internet that will help me using that sensor, so it's easier for me to use. And
Yeah, can you go to your test 2 results? This one here, I noticed at 4 p.m. the power consumption dropped to 2 watts and the current went way up to 200 milliamps. What happened there?
It's just 2 amps, 2 milliamps. Sorry about that.
Oh, it's just a typo.
Just 2 milliamps. It's 2 milliamps.
Yeah.
Yeah.
Alright. Any other questions?
It's 10:15, so.
Alright, thank you, Jed.
Okay, thank you. It's already been created, so it's good.
I'll leave
That's a lousy excuse. Yeah, that's a lousy excuse. I have to go up, or the teacher has. Yes.
This is set up, you don't have to switch. So you don't have to switch in between.
Where were you?
Between your presentation, like presenter view. Okay, you don't have to change anything, just start the show. And then when you want to show, maybe you practice this already, and you want to show the camera view, it's all there, right? Okay. So it should be all ready to go. Yeah, if you want to open up our document, you can do that. We'll get up and take a little more. Freds.
Yeah.
That's what happened for you all.
They're there, but. It's still a surprise, there's something. Yeah, the one.
I just created that.
It works. But if I try to look which has the URLs that are on the schedule,
So what I do is I just,
yeah, so that's why. I was hoping to follow on, and there was no way. It's gonna be like a plot.
yes, and the guy has like, I get inspired by that.
I would very much,
Well, I can make anyone you want, but it's saying. Yeah, I'm gonna do that. I'm gonna do that today. Expired. Yeah, I'm gonna do that today. Anyway, if you have time between now and the next, I didn't have your contact, but if you want to send out the URL that I'm using, and they can clean, but they can also watch, it'll still be able to watch after.
I don't have to hear.
Yeah.
You want me to do that?
Oh, I don't care, like, if you want. Just if people are trying to watch, they're not gonna see anything right now. Because they won't be aware of the, URL. Yeah. Oh, I don't know who's responsible for the close line. Oh, there's one here. Oh, there's one. Yeah. There you go, yeah. You have to bring your own pen.
So, Ron, do you want me to, do that? I guess so.
I don't know if anyone's planning on watching it on there. They won't see it unless they get, and I don't have the contact. Or else I would have done it. That was the quick solution to get it going. Yeah, whatever. We'll just do that one. We'll just say apologies for the late notice, but we had to go with the URL for tonight. I don't know why there must be some difference in the setting between what OBS is setting up as a screen setting and using defaults and everything.
Yeah, I usually.
Yeah. Well, it isn't as long as it isn't once you go and use whatever settings that I used to set up. I just didn't do anything. Yeah. We take it at random throughout the morning. Yeah. Yeah. So we just come in through the back door. Yeah. It's just our memory.
Cleaned up.
Yeah.
That's cool.
See the comment?
See the comment?
I actually haven't thought about it. I thought about it, but I haven't really. One thing we could do is just use a device like this to go and Oh, yeah. Yeah, so you want to use the projector over there. We could look at that at lunchtime. Tomorrow. We can look at that later. Okay.
I think it's the lighting was dimming too.
Yeah, it is. Yeah. It doesn't like that. These aren't actually, you spend enough money on those, but they're not that great.
This is like a speaker and camera.
It's
Sticky.
it is actually. I just have it adjusted to just be on the, well, one thing we can do is we can do this. Oh, actually it's stopped.
you're gonna split the. Yeah. Now you're gonna split the screen. You need to show the e-press.
What's that? It's great to have people who like to ask questions. Less pressure on one person to come along. Actually, oh, I didn't even know you came in.
They see me back.
Shapeless soul. I didn't know you guys.
When you started out,
Tuxedo t-shirt, shorts, flip-flops, and a fit visors. The ultimate swiner. Oh no, I'm starting to. Dude, he was just like ass gloves or pull like a bomb trying to set it. Feel like I eat fishes. Oh no, it's just the disrespect.
yeah. I'm going to get out of this. I want to put it right You're almost. You're outside now? You just gotta remember.
I'm just gonna try not to think about
I already have to.
saying, especially roll their mask. Roll their, got to get something. Oh yeah.
I don't know, I like so bad. You like my consequences. There's nothing
Well, that's
Okay, this is time.
Okay, so our next presenter is Mr. Alan Pop, and he is going to present his USB mechanical keyboard.
Hello everybody, I'm An, and today I'm going to talk about my USB mechanical keyboard. So here are my main points. I'm going to talk about the functional overview, technical overview, PCB design, 3D design, some issue that I have, the testing procedure, and finally the conclusion of this project. Okay, so why choose a mechanical keyboard over others keyboards? So there are a few benefits that mechanical give you. So mechanical keyboards are customizable. The switch can be changed out. The keycap can be changed out. The key layout can be changed either through the program itself or changing the PCB. And well, I chose to make a mechanical keyboard because I want something special, which in this case is a 60% with 64 keys. There is not a lot that you can find on the market that have both 60% size and is compact, but then also include the arrow key as well. There is also customizable macros and shortcuts. So there is a firmware that called QMK that you can use to program the Atmega family MCU for only keyboards. There are N-key rollover, which is the ability to press multiple keys at once that others commercially keyboard, like an office keyboard would have rubber membrane, doesn't have the ability to do that. And it also have anti-ghosting, which I will talk about later on in the presentation. So what is the USB interface? So it is the universal serial bus interface. It uses 2 data lines instead of 1 like serial. So we have D plus and D minus. The state of the combined data line will create a different output state for the computer to receive. So in the chart you can see D plus and D minus. When both are 0, you get output state of 0. When D plus is 0, D minus is 1, you get K. When D plus is 1, 0, D on D minus, then you get J. And when are both high, then the state is 1. And this means that you have 4 possible data values to use to transmit your data to the computer instead of only 1 data line which only have high or low, like serial communication. There is also one more benefit, which is speed. Because of the amount of data that you can send, there's way more bit that you can send at a time. So a typical USB 2 would be able to send 480 megabit per second, which is pretty fast. So here is my block diagram, and I'm going to divide it to 2 sections, the input to the MCU and the output from the MCU. Okay, let's look at the input. So I have 4 input here. Firstly, the user input. User input into the mechanical switch by pressing a button within the switch matrix. So my switch matrix have 64 switches with 64 keys on the keyboard. And then there is also an external crystal oscillator that is used because the MCU requires it to operate in USB interface. There is a reset button, it used to either power cycle the keyboard, or it can use to enter DFU mode with our a special mode on the Amiga 32U4, where it is you can program the MCU itself through the USB interface instead of a serial communication using a picket like a typical Amiga 338P. And lastly, I have ICSP, in-circuit serial programming, which also include if in case the USB fail, then I can upload the code to the ICSP protocol. Okay, next. So the USB-C here is to connect it's a data line. It's act like a bus. There's 4 wires, D plus, D minus, V bus, and ground. So the D plus and D minus transferring data from the MCU to the computer, and from the computer back to the MCU. It also acts as a power supply here. Provide 5-volt input for the keyboard, so when you plug it in, the computer itself is powering the keyboard. So it also includes a catalog indicator, which is an LED that is underneath the caps lock key that turn on when the cap lock is toggled and turn off when the cap lock is off. So let's move to the technical overview of the project. Here is my overall schematic. Next, I have the external crystal oscillator. As I mentioned before, this is a must-have for the user to be able to use USB interface. So from the datasheet of the Amiga 32U4, an external crystal of 16 megahertz is required on pin 16 and 17, also named crystal 1 and crystal 2. And the crystal itself will be connected to 2 balancing capacitors. This can be in a range of 12 picofarad to 22 picofarad, which I calculated to be 13 picofarad, and I have tried using the 12 picofarad, but the crystal doesn't give out any clock signal. So that's why I go with the 22 picofarad capacitor, and it gives output clock for me to be able to use the USB interface. The problem with my calculation is that I couldn't find any particular data sheet that contained the input capacitance of the pin of the 32U4 MCU itself. There is document recorded for different Amiga chip, but I couldn't find any for the particular one that I use. Okay, next we have the in-circuit serial programming port, where this is designed to be used with a picket 4, and the pin layout can be viewed on the screen there. Reset, connect to reset, MISO, connect to MISO, and then you have VCC and ground. This is only to be used to re-upload the DFU bootloader if it have faulty issue, or the USB recognition, HID recognition that failed, which means the computer itself cannot recognize the keyboard when it is plugged into the machine. For now, I don't think I can program the keyboard itself using ICSP. I have only been able to use it to upload the DFU bootloader itself, and use the DFU bootloader to be able to program the keyboard. because the QMK, the make file only make file for the DFU bootloader. Okay, next I have reset switch. So it is connected to a pull-up resistor, and when you press the reset switch, it's gonna pull all that to ground, and the reset pin gonna read low. And then that, if the pulse of your press is longer than the pulse of the internal clock, then the MCU power cycle basically turn off and back on again. And it's also, if the MCU is programmed to enter the DFU mode when you hold reset and connect it to the USB. Okay, next I have the USB-C connector. So here there is a few requirements for the USB-C connector to be able to work. There has to be two 22 ohm resistor on D plus and D minus side, D plus and D minus line. On CC1 and CC2, there must be two 5.1 k ohm resistor, pull low to ground. And let's have a broader view. Pin 33 HWB must be low for the USB interface to work, and the UCAP, which is the capacitor pin for the USB itself, have to be connected to a 1 microfarad capacitor to work. There's a few more, which is 5 volt must be connected to V bus, and pin 7 NBCC. That is for the USB monitor system on the MCU to be able to work. Well, I learned it kind of the hard way that I will talk about later on. Next, this is a simple circuit for a lighting turn on and off an LED. So if the cap locks is to be toggled, then the pin gonna output high, turn on the LED, and vice versa. If the cap lock is read low, then the pin gonna be low and the LED gonna turn off. Okay. So in my circuit, I use only one 5 volt bus, and it is power coupled using capacitor 1 to 5. The reason why capacitor 1 is 10 micro instead of 100 nano is because that's the first, it's like the master power couple that filter out most of the voltage spike, and then if there's any more smaller voltage spike, then the rest going to be filtered out when it enters different pins that is connected to capacitor 2, 3, 4, and 5. Okay, so here is my switch matrix. So to be able to work with a keyboard, you have a lot of keys, 64 keys to be exact in my case. But there's one problem, that the MCU, the Amiga 32U4 only have 44 pins. So you cannot connect like one switch to each pin because 44 pin wouldn't be enough, and that is including all the voltage pin, the data pin. So a switch matrix is a solve to that. So what switch matrix is like a grid system where the column and the row meets. There's gonna be a switch, and it's gonna have coordinates like so this can be 0.0, this can be 0.1, and moving on. And the switch matrix are connected to the MCU. I use 5 row and 14 columns, so that add up to 19 pins. This can be reduced if I change it to a square, but this is the easiest way to visualize that because the switch underneath here is connected exactly to that layout in the on the switch matrix. So let's talk about anti-ghosting. So ghosting is a phenomenon where in keyboard, when 3 or more keys in the same grid, for example, this 3 key, when switch 1, 2, and 16 are pressed, the current will flow from column 0, column 1, and row 0 and row 1 gonna read. So it do it by pulse and send 1 current, read, 1 current, read. But there's a problem where the MCU cannot recognize the exact 3 key that is pressed because the coordinate can be created by different combination of the 4 keys in the matrix. So a solve to that is use a diode. So as you can see, D1, D2, D15, and D16. It only allows current to flow in one direction, prevent the current from flowing backward into a switch that is not pressed. And this is called an anti-ghosting diode. So here is my software flowchart. You can look closer into that. So here I have start, initialize keyboard, check status of the keyboard and MCU. So this is to initialize the switch matrix itself, loading up all the requirements, figuring out what OS the keyboard is connected to. Then it declares USB interface library. So that is all included in the platform setup. The protocol is for declaring USB interface library and switch matrix. Next up we have, so it needs to set up communication between the MCU and the computer. So it do that by firstly setting D plus high. So when I connect the keyboard to the computer, D plus going to be high, and then the two D plus and D minus gonna oscillate, and that's to sync the internal clock of the keyboard itself to the computer, and in that way it can have data transmission, where a data package is going to be sent from the keyboard going to the computer, asking if there is a host. Then there's going to be a reply from the computer back to the keyboard, say yes, there's a host, and then they do a handshake protocol, which they recognize each other, and then that's where the keyboard can input information into the computer. So I have here is the scan matrix for switch inputs. As I mentioned before, it do it by so each column send out a pulse each time, one column at a time, and then they set the rows to read. So they're gonna send pulse, and then the row is gonna keep reading, and then if there's a short in the switch matrix, it detects where the short is because it can detect like from what pins the current flow into what row, and then you can get that coordinate and to transfer that to data that can be transferred to the computer to USB. So next I have caps lock. Because I have a cap lock indicator, I want to look more into this. So basically it's gonna check for cap lock boolean status from the received input key. So if it is going to keep checking for it from the computer itself, the computer itself holds all the information of the switch. This only acts as a translator that translate your input. So it translates that into the language that the computer itself want to decode and then translate to a character on the keyboard. So here is my concept drawing. The key layout can be viewed here as well. As you can see, the ship on both sides is shortened. That's how I was able to shrink the ship on left side and right side to be able to fit the up key and delete key. I also shrink function key, control key to be able to fit 3 more arrow key. So this is the component structure assembly, as you can see. So on top, the keycap going to attach the switch. After that, the switch, the whole thing is placed on the plate, then the BCB, and then the switch is soldered underneath the BCB, and then that is put into the case, and it is screwed into the case. So I want to talk about a little bit about my 3D design process. So this is the first time I ever touched 3D design, and I wanted to design my case. So I learned that we have to create a sketch of the project with the exact measurement that I measure in my concept drawing and my BCB itself. And then input that into Fusion 360. Then I use the extrude to create walls, support, and mounting holes. Next, I have to export the file STL, and then use the Make a Print app to create a print file that is only used by the MakerBot print 3D printer in the lab. So next is BCB design. My project is really heavily based on the BCB itself, where there is a lot of things I have to consider. So surface mount is my choice because it is to save space. They are lightweight, and the switch gonna be mounted on top of the BCB. So therefore, if I choose through hole, and I mount the component on the back side here, and then stick out the pin on the top plate of the BCB, then that's going to interfere with my switch placement, where I cannot push my switch straight down flush into the BCB. And the plus and the minus must be equal length because they are a differential pair, which means data transition and they oscillate at a really high frequency. So, but then most of the time they oscillate at a opposite pulse. So that's why they cancel out the impedance when it switches so fast at 480 megahertz. So here is a better look at my BCB design. Well, everything is on the back side, so there's nothing much in the front cover, only that LED spot for my cap lock LED is on the front because that's the only way I can show the LED. Here is the back, so let's take a closer look. So the MCU placement is to optimize the connection from the MCU itself to the USB-C connector, where I only have so much space underneath the space bar. So that's why I choose that position to place my MCU. And as you can see, my D plus and D minus sign should be in equal length to prevent any impedance. Next up, the power coupled capacitors must be as close as possible. So it look a bit clustered, but that's the best I can make it since it has to be close to MCU. I cannot trace it far away into like a clearer space to mount the coupled capacitor. Next, this is my final PCB product. As I talked about before, I learned something the hard way where I delete the pin by accident. I have to jump that to 5 volt. Here is my test number 1. It's the maximum current draw test, where you need a multimeter, connect and a sacrificial cable where you cut, and then you cut the 5-volt line in half, and then you hook up your multimeter in series in the 5-volt line. I would rather put the cap lock on because the LED also draw a certain amount of current, and I would keep that cap locks on to test to see what's the maximum current draw of the keyboard is. So I find out that the maximum current draw of the keyboard is about 37 milliamp. Next is the key input responsiveness. So here I use a software that is about that have the clock signal and then the data of different keyboard that it can compare my keyboard to. So basically what it does is it look for the polling rate of the keyboard itself, and then from that it's gonna calculate the cycle time, and then so basically the keyboard can only input a signal every time a cycle is completed. So in this case, the polling rate is 1000 Hertz. So the cycle time should be, so only a switch can only input every 1 millisecond. And then from that, it can distinguish like when is the start and the end of a cycle, and then it can detect your switch input in between those, and then it can calculate your delay for the switch input. So my average delay time, which is 0.23 millisecond, which I don't think it is too bad, and the polling rate fall at 1000 Hertz, where a typical keyboard is from 500 to 1200, where I would say that's a successful attempt for me. So some issue that I encounter. So my 3D print, it warp a lot because the printer in the lab doesn't have a heated bed. So I try to solve that problem by increasing the chamber temperature and then adding tape for better bed adhesion so the thing don't lift off when it cool. So there's sometimes that the filament is slipping where you just have to fit it back into the extruder. As I mentioned before, the crystal oscillator do not output signal for me once when I use the two balancing capacitor, that is the 12 picofarad. And then, well, one of my BCB, the trace on the USB-C broke off very easily, and that's like a big problem. So the estimated value for my project is about $300 initially. The final costs only turned out to be $112. And I have some future consideration. I want to add backlight, reprint the case, remake the BCB, fix the mistake that I made. And I also gained a lot of experience in BCB design, 3D printing, and surface mount soldering. So here is my reference. And I want to demonstrate. As you can see, I can input by typing. So I can type, hello, everyone. I'm sorry. Smiley face. And then cap locks. So when you turn the cap lock on, the LED light up and it shows that cap locks is on and the cap locks is on. So when you type something, it's going to be capitalized. So for key rollover, I set it to a typical mechanical keyboard have like 6 key rollover. So I can input like 6 key at the same time. 6 key. And it's gonna input 6 key every time at the same time. And control, save, function keyword. And here is my ICSP. So it is mounted with a cover. So if you want to access, you remove the tool screw, lift the cover off, and the pin should be revealed. Here is the reset pin. So if you want to reset the keyboard, just stick and press the button inside. The keyboard should turn off and back on again. Okay, thank you everybody. That's the end of my
Mr. Haw, you did a good job of presenting. We got a few questions here. Let me just- Can you bring up your slide that had that talked about the circuit serial programmer
Okay.
schematic?
Yes.
So you mentioned that this is a backup, and I thought you also have a requirement in a lot of projects here that have MCUs for being able to program the MCU. You mentioned, you said here a few pins, NBCC, ground, MISO, MOSI, SDK, reset. What's MISO and MOSI?
I can't remember exactly. It is two big information pin.
It's what, sir? I just didn't catch it. What would you say?
Information pin.
Information? What do you mean by information?
I'm sorry, I didn't look into it.
What's SCK? No? For your project, you should maybe know. Right? All right. You also mentioned the reset configuration there for your MCU.
Yes.
You said it would cycle, power cycle, which is correct. And you got that 10K resist there, R1. Why did you feel a need to use the 10K resistor, not the internal pull-up resistor of pin 13?
In the code itself, there is no, so I mentioned before I use in Q&K, so there is no place that I can input the actual like internal or external,
Okay.
so I have to use the external.
Okay, that's fine. I was just wondering. Well, I got a few quotes here. I shrunk keys. Bring up your key layout.
Key layout, okay.
So you said you shrunk which keys?
I shrunk the left shift, the right shift, the function key, control key.
Okay, so you use the flux gate defibrillator to do the shrinking, or?
Oh no, I mean it's the actual size of the keycap itself. So I
Okay,
had
so
to,
you shrunk it.
No, I buy a shorter. Yeah, the manufacturer that produced the.
So you bought a
a
smaller
modified
Exactly.
keycap set.
Because I shrunk, we can believe that.
Sorry.
You have some kind of shrink machine. Your layout there, the bottom layout of your PCB. You talked about differential pairs. Which ones are differential pairs?
It is.
Yeah.
It is that 2 wire right down here.
Okay. And it needs to be differentially paired. Why?
It is because the tool is data pins, so it's switching frequently, and then that switching create impedance because it acts like a.
The switching creates impedance.
No, so you have 2 wires, which must be equal length, so the data input can receive at the same time.
Okay,
Which
so
not
that's not in, okay, so what's that term called then? If you're receiving data at different times, do you know what term is called?
Delay.
Well, it's based on propagation delay, but there's a term for it. As far as the receiver is concerned, it's called skew. Right, so skew means you're getting data from one slightly slower than the other one. Okay, what's the problem with that?
So I have to make it equal length and
Why?
closely together.
Why?
How do I say it? When the 2 are switching, it's create. It is like a inductor where it create impedance. So when you do that, it's like a twisted pair where the 2 wire can cancel out the impedance. Like I mentioned before, like before every protocol, they do a sync sequence, where one go high, the other go low, switching like that. Then if they do that, then they.
So why don't we just tie on the ground, forget that, and just do single-sided unbalanced pair, or unbalanced.
So that's gonna create a more impedance on the line, since if one is switching like that, then.
Same switching. You only got 1 wire, same switching.
Oh, 1 wire?
Well, why don't you just ground 1 wire?
Oh, if I ground 1 wire, there's no connection to the plus, or it's
I
either
know,
the plus
so,
or
but
the
I'm
minus.
asking, what's the benefit of doing this versus, which is balanced pair, versus unbalanced pair? Right, you could have just ran 1 wire in the ground, but you ran 2 wires in the ground.
Oh, because so I can have 4 value, like I mentioned in the
4 value?
first USB slide.
Bring the slide up, because I don't understand what you're saying.
Because I don't understand that, like one is pull low with a switch or something like that, but then there's two connection to the plus and the minus.
Show me your slide, I'm not following what you're talking about.
So here, so the plus and the minus must be connected on the 2 pin in the NTU. So if one is pulled to
No, that's not true.
Oh.
That's not true at all. That's why we put a big X on that. That has nothing to do with this. That's false. I
okay.
didn't catch that. All right, you need to look into obviously differential pairs and how they order. Could you also bring up your flow chart? I have a few questions, but I'll only ask one and I'll leave the rest. could you bring up the checking the key caps, the caps lock? No. So the diamond symbol means what? What does the diamond symbol mean?
It's like an if
Yeah, it's a decision-making,
decision making.
right? So really the box before that check caps lock Boolean status really doesn't belong there. That's the decision being made there, okay? What decision is being made there? What outcome is altered? And when the decision is made, what do we do after?
Oh,
So what decision is made?
so it's gonna check for the bits that in the data package that include the caps lock toggle state.
Okay,
it's a Boolean
so if it's
1,
false,
0,
what does it
1.
do?
It turned off. I made a mistake there with it off there.
Okay, okay. And then what does it do?
Then I keep checking.
And when does it stop? Keep checking.
I don't. I read the code and I do some research. The keyboard itself going to keep scanning, even though.
No, but let's talk about the flow chart here. The flow chart is your observation of it. Let's look at your flow. Your flow chart on the left-hand side. You're coming into that decision-making process. Let's forget the keyboard, okay? It's coming into that decision-making process. It says, is the caps lock toggle? It's true or false, right?
Yes.
And if it's true, it turns the LED on. If it's false, we've corrected to say it turns it off. And then it goes back, and what does it do?
It goes back and it.
Does the same thing again, right? That's what your flow chart shows, right?
Yeah, it keeps checking.
And it's true or false, and it goes back, and it goes back, and it goes back, and it goes back. And let's just sit here for a million iterations of this. When does your keyboard do anything else now?
Also, it should return.
It may have to do it every time something's happening, but if it's doing it every time it just checks the caps lock, it's just going to go around in circles and stop there. And if you hit the key at the wrong time or whatever, it'll make that one key happen, and that's it, right?
As I mentioned before, it's gonna the polling rate. It's gonna check.
Yeah, but it's going to be
everyone.
stuck in that forever.
What happens if I push the X key
Yeah.
and it's stuck in this loop of checking caps lock?
Oh, it's a separate outside loops.
Well, I think there's interrupts probably that are in play here that
Maybe.
have to be breaking up your flow chart
Yeah.
here. But still, it should be obvious to you as you're looking at this that there's no out to your logics, therefore it must be faulty in some way, right? Anybody else want to?
Well, I had a question about the cost discrepancy between your projected cost and the actual cost. How come your actual cost was like about 1/3 of the projected cost?
Before I calculate for the keycap itself, so I was looking. So I have the smaller keys, right? I was looking for a set that is quite more expensive. I couldn't find any cheaper one, but then at the end I find a cheaper alternative. So I checked the production price of my BCB as well. At first it is like $30 to make my BCB, but so because I have an let I show. So I think Mr. Metcalf told me to change it before because I put my my USB-C port outside, so it add a lot more production cost to the BCB itself. When I sunk it in, it's a perfect rectangle, so that cut it down a lot by $30 alone on the BCB.
Yeah, that's interesting, thank you.
Did that include shipping?
$30 no.
So how much did the shipping cost you?
Um,
Everybody's bragging about $5, $10 PCB boards, and I'm talking about the $80, $85 of shipping.
for me, so I ordered my VCB with someone else. So we split it. The initial cost of the shipping is $40, but I have to also to pay custom $30 more.
So we're now at $70, I think. True, it's split, it's
Because
still.
shipping doesn't count into the.
Oh, yes, it does.
Yeah.
Yes, it does.
It's
That's
not on
for
the,
free,
it's
right?
not on the parts list,
Yeah,
but it
yeah,
still
it's not on
counts
the
if you
parts
gotta
list.
sell this thing or whatever.
Yeah.
Yeah, yeah. Okay.
Can you bring up the example of your code for a second?
1 minute.
Yep.
Which one?
I don't know, you have the header part of your code there, the initial
Oh.
part of the code.
I only have part of my code. I don't have the header. Like this.
Yeah. You have a pre-compiler instruction, if def. What does that mean? Do, live, eat, breathe.
So it's gonna check a define. So what QMK do is it have a quantum file which contain all the key mode, and then what this do is it's going to check in that file if for example, if that quantum painter mode is enabled, so if the bit is 1, then they're gonna run the quantum painter task, where those tasks is a lot of modification that you can make on your keys, where the backlighting, but mine doesn't have any shortcut macros.
And if
something
it
like
doesn't
that.
find it.
If you don't enable any of the function, then it should be 0, and there's no need to run that.
Well, no need, it won't.
It won't.
It decides whether it should run that macro or not
Yeah.
macro in this case.
It's a separate script.
Yeah, well, it looks like to be a function prototype there, right?
Yeah.
Okay, so it's telling us whether it needs to, it's deciding what it needs to do before the code's ever compiled, right?
Yes.
Okay,
Thank you.
thank you.
Thank you.
How are you?
What would you like to use for this? Let's just do it.
I have
Yeah. Yeah.
I was in here yesterday.
That's fine. I should have pushed.
I found something I didn't think of.
I know.
Turn out.
The other ones I guess on most people are providing I just said it, so it's. There's what it looks like. So as long as he stays, most of the things the L's. I just say, just said it. And it's hard to do.
Yeah.
Especially if we're strip on the top. I just want it there. If you could zoom a little bit more, that'd be better. Your desk is a little bit more You'll see it on 30 seconds here. Put in, if we were going to go this way out, this way over here, put it in the Swiss area. First, it's over by 200 books over whatever it is, because that rate goes on for and then you have this, yeah.
Okay, our next presenter of the morning is Al Garcia, and he'll be presenting on his project of cold temperature effects on battery storage capacity analysis.
Thank you, Mr. Brown.
Okay.
Okay, so good morning, everyone. My name is Aljon Garcia from the Electrical Engineering Technology of the Atomic Energy Program. And today I will be taking you through my analysis project on how cold temperature affects the storage capacity of a battery. So, in this project, I will be talking about the purpose of my project, some concepts, my assembly overview, and the analysis results, conclusion, future recommendations, and lastly, a demonstration video. So, in today's world of technology, the world is progressing to the evolution of renewable energy for a much more sustainable future. Deep cycle batteries have a vital role in the advancement of renewable energy systems that allows us to store energy. As the sustainable energy expands, we can only expect that deep cycle batteries will only continue to increase in demand and will only continue to evolve to have a much more reliable and efficient energy storage. Deep cycle batteries have a wide option of applications, such as the PV applications, and it is also used in the automobiles and electronic devices. And all of those commonly uses lead acid batteries and lithium ion. However, we live in the North America where the climate is very diverse and renewable energy collides with the cold temperature. Imagine a cold winter morning when you're about to leave for work or school, and you hop in your car, you start your ignition, but the car suddenly wouldn't start or struggles to start. And then you pop your hood, you're trying to troubleshoot the problem, maybe scrolling through your phone, looking online, what's the problem? But then you also notice that your phone seems to be draining fast. This scenario has got me wondered, how does cold temperature affects the storage capacity of a battery? In this analysis project, I will be comparing lithium ion versus lead acid battery to observe how their storage capacity is affected by the cold temperature. So, what is the storage capacity? Know that storage capacity is the amount of energy that a battery can store. By using this formula, C represents the storage capacity in amp hours, and we can calculate this by multiplying the discharge current to the time of discharge in hours. Take a 12 volts and 100 amp hours deep cycle battery as an example. So here you can expect that the battery will be discharged in 1 hour using a 100 amp load, or 2 hours, within 2 hours using a 50 amp loads, and so on. But it is almost impossible to discharge the battery in exactly 1 hour using a 100 amp load due to its internal resistance, which dissipates heat, meaning that the higher the discharge rate, then the more loss you will have. So there are other factors to consider when it comes to the storage capacity. Other than the discharge rate, there's also the temperature and the depth of discharge. Depth of discharge basically means it is inversely proportional to the state of charge. For example, your phone, when it says 100% battery level, that means the state of charge is 100 and the 0% of depth of discharge. Whereas when the battery is at 70% state of charge, that means the depth of discharge is 30%. So focusing on the temperature, which is the main focus of my project, referring to the data sheet of the lead acid battery that I use in the section of temperature effects in relation to battery capacity. This graph shows that how cold temperature affects the maximum storage capacity that your battery can store. So looking at this one, this means that when you discharge your battery for 20 hours at its rated temperature of 25 degrees, you can have over 100% of its maximum capacity. Even at 10 hours of discharge rate, you can still have 100% of maximum capacity under its rated temperature of 25 degrees. However, that all changed when you go down to its cold temperature. So as you can see here, when you discharge the battery for an hour, even at its rated temperature of 25 degrees, you can only get about 55% of its maximum storage capacity, and down to 20% when you discharge it at negative 20 degrees. So after considering those factors, I went ahead and decided which battery I will use. Since I am doing an analysis project between the two batteries, it only makes sense to use batteries with the same ratings. In this case, I scaled down to a smaller batteries with 12 volts and 6 amp hours lithium ion and lead acid batteries. I took the same concept and decided which discharge rate I will be using throughout this project. So if you can see here, the same concept, discharging it for 6 amp should be discharged at 1 hour. But in this case, I decided to go for a discharge rate of 1 amp, just because I know that the time is limited for me to discharge the batteries for 20 hours or even 20 hours, since I am performing not only one but multiple tests. So I had to consider the time. Also, I didn't want to use the 1 hour, since I know that the capacity will greatly reduce when I discharge it for only 1 hour. And it could also potentially damage the battery due to the repetitive discharging trials, could reduce its maximum storage capacity. So since I decided to use a 1 amp discharge current throughout the project, I had to consider the effect regarding the temperature. So from the data sheet that I used from the lead acid data sheet, I estimated the graph, the curve for the 1 amp discharge rate. So estimating the value at negative 15 degrees Celsius of 1 amp discharge rate, you can end up having a maximum of 60% of the total storage capacity. And at 20 degrees, which is a room temperature. So as you can see here, even at the rated temperature, using a 1 amp load could already change the maximum capacity you can have. However, as I was considering these external factors, lithium ion somehow didn't provide a graph indicating how temperature relates to its battery capacity, which was a mystery that I wanted to unveil. Moving on to my block diagram. For the data capture, the lithium and lead acid are the main subject of my project, which will be the one that will be observed. Connected to a shunt resistor for current measurement purposes, and the variable load that I use, which is a constant load that has a capability of discharging between 10 milliamps all the way up to 20 amps of discharging load. But I only used 1 amp in this project. All measured by the 4-channel DAC to gather all the data that I captured from the test, and that'll allow me to transport all the data that I captured from the test to a CSV file for a summary. And for my project, my concept was the ambient temperature, so I only use a thermometer to monitor the temperature where the battery will be discharged at, and the timer, which just to time how long it will take to be discharged. Okay, taking a look at my concept drawing here, my components are placed in a plastic enclosure just to avoid it from possible water damage. And remember that the DAC must be connected to a laptop, which has a Windax software to allow the user to record and monitor all your data from your test, which in this case I use to monitor the voltage of the battery as well as the current. And the battery here is discharged under cold temperature, which in this case I used the deep freezer just to simulate the cold temperature of the winter months. And my leads here has to be long as possible, since I was placing the battery inside the freezer and I need access to my components and the laptop. Okay, so this is the finished build of my project. So the battery under test connects to the binding post, the thermometer that I use to monitor the, I forgot to change it, but this is the shunt resistor, the DAC. And the thing about my enclosure has holes already, so it was easy for me to access the DAC and as well as the load, since it has to be connected to an wall outlet. So the test that I have conducted consisted of 4 tests. The first one is the discharging test at negative 15 degrees Celsius, and second was at negative 10 and at 0 degrees, and the last one at ambient temperature. All of it was discharged using a 1 amp load and discharged down to its recommended cutoff voltage, referring to the data sheet of the batteries. So taking a look at the discharge curves of the batteries that from my analysis. So since a theoretical value of the lead acid under 20 degrees should give you an approximate of 5.1 amps, I only ended up having 3.92 amp hours under this condition. And at negative 15, the theoretical value I should get was 3.3, however I only have 3.12 amp hours. And for the lithium ion curves, here is the discharge curve. And as you can see, at 20 degrees, I ended up having 5.38 amp hours. And even at negative 15 degrees, the battery storage capacity was still over 5 amp hours. So moving on to my analysis results. As you can see here, at negative 15, the lead acid only have 3.12 amp hours, whereas the lithium ion have 5.08 amp hours, which is very significant when you're comparing the negative 15 ambient temperature to the 20 degrees you can see that the lithium ion still retained its storage capacity up to 5.38, and the lead acid only having 3.92 amp hours. Looking at this graph, you can see how the storage capacity of the battery was decreasing as the temperature decreases, and vice versa, the storage capacity increases as you increase the temperature. The analysis summary. So lithium ion was somehow managed to retain over 80% of its original capacity, and that is out of the 6 amp hours, unlike the lead acid battery that only have over 50% of its original storage capacity throughout my analysis. So, in conclusion, it is obvious that the lithium ion could retain over 80% of its original capacity regardless of the temperature and the discharge rate, whereas the lead acid only retained about 50% of its original capacity. However, there's some external factors that could have affected my analysis. We know that the lithium ion has a depth of discharge capacity of about 80%, unlike the lead acid battery that can only has a recommended depth of discharge of 30 to 50%, which could be the reason why the result shows that lithium ion was able to retain about 80% of its original capacity. So, which one is better? That all depends on the application you will be using. So if you are using your battery or any application under cold temperature, the lithium ion is a great option. However, the price and the size must also be considered. But overall, both batteries perform great. So if you are planning on using your battery under around rated temperature of above 20 degrees, I think lead acid is still a great option to consider. Some limitations here: the batteries were only rated between -20 and 50 degrees, meaning I cannot go under and beyond those range due to the battery's internal chemistry, because we know that the chemistry of the battery slows down at when it is cold. And so my limitations are temperature limitations. The temperature control was the most challenging part of this project, since controlling the temperature is out of my control. Even if you perform the testing outside, it's obvious that the temperature is not constant and it fluctuates, so that could still affect your results on how much storage capacity you will have by the end of your analysis. So what could be done to improve? There's a lot of things that can be done to improve this project, such as using a thermocouple instead of just a normal temperature to monitor the temperature of the battery, and it will also allow the user to monitor the temperature of the battery, and they can use that to estimate how long they should leave the battery inside the freezer to reach the temperature equilibrium between the battery and the ambient temperature that it is under. And that is the end of my presentation. And to demonstrate this, I I only provided a video since I don't think any of us would like to wait like 6 hours, 5 hours here to complete the analysis, and I will be showing a quick demonstration on how I performed the test. That's my references. Sorry, excuse me, is there a sound for the...
Yep. There's a sound bar here and the, you just have to turn it on, there's a button on top there. It's Bluetooth, so.
There's no sound.
Just make sure the volume's turned up. Just go to the taskbar in the system tray and look for the volume icon. If you move your mouse to the lower right. Yeah.
I heard something.
There may be a volume control on
It's ringing
Sorry,
I'm not sure how to connect the...
it looks like it's connected because when you were showing the volume control there, it said Polk Audio, which is the brand of that unit. So. There it is.
It is important that both batteries are fully charged before we perform the discharging test of both batteries. A thermometer is used to monitor the temperature. Let the battery cool down for about an hour before the discharging test. After letting the battery cool down, the test can now begin by connecting the battery to the electronic load and set the desired discharge rate, which in this case will use 1 amp of discharge rate as discussed. And we will time it until the cutoff voltage is reached. So after about 3 hours, the voltage is now down to 12.1 volts. So after about 5 hours and 8 minutes, the battery has now been discharged down to its respective cutoff voltage of 10 volts. We can now record the data. We can now go ahead and let the lead acid cool down in the freezer before we perform the discharging test. Just like the previous test, we will have the same ambient temperature and let the battery cool down for a fair experiment. After letting the battery cool down, we can now go ahead and perform the lead acid discharging test. Just like the previous test, we will set the discharging rate at 1 amp, measured and timed until the cutoff voltage is reached. After 2 hours and 18 minutes, the voltage has dropped to 11.44 volts. After 3 hours and 14 minutes, the cutoff voltage of the lead-acid battery has been reached. We can now go ahead and export all the data from the WinDAC software to Excel and summarize all the data we have gathered throughout this experiment. By the end of the test, the lithium ion was able to retain 80% of its original capacity, unlike the lead acid, which reduced 50% of its original capacity. To end the demonstration, I hope this gives you an idea of how cold temperature affects the storage capacity of lithium ion and lead acid battery. Thank you for your attention.
Yeah, I got a question. You mentioned you chose a plastic enclosure because it's waterproof characteristics. By drilling large holes on the side to feed wires in it, is it still waterproof?
Well, that's the thing, because I need access for the plugs of the electronic load, because I need to plug it into a wall. Also, the DAC needs I need access to the hole to plug it into the
Right. It wouldn't be waterproof anymore.
not fully.
Was it ever waterproof?
Sorry,
Was it ever waterproof?
the enclosure you mean? Well, I just bought it from a manufacturer, and it's an IP60 rated at IP65.
So is that waterproof?
Water resistant. Sorry,
Thank you very much.
water resistant.
Thank you very much. Nothing is waterproof.
That's right.
What was the title of your project again?
The title of my project was the effects of cold temperature on their storage capacity.
You mentioned a lithium ion battery. Is that what you use?
Yes, lithium ion, specifically lithium iron phosphate.
Lithium ion and lithium iron, is that the same thing?
Well, it's a type of lithium ion.
While we're talking about that then, you bring up your initial data there, you get some graphs.
My results, you mean?
Oh, yeah, yes.
Here.
Sure, yeah, okay. The question I had is, you started off with talking about the theoretical discharge rates and capacities, and said, I can discharge at this rate for an hour, and I can discharge at this rate for this hour. And then you specified why you picked whatever rate, and that's fine, I had no problems with that. But then you found the results, you gathered results, okay? These ones here specifically, and I think you mentioned in your presentation you got nowhere near theoretical results. Can you maybe speak on why that's not unexpected based on your test conditions versus that single number of battery capacity, the theoretical?
Yeah, since from the beginning of the project, the slides, referring to the data sheet of the lead acid, I estimated the maximum capacity that I will have. Considering that I am using a 1 amp discharge load, which will already decrease the storage capacity that I can get. So here, I am theoretically, from the graph, I should get 5.1 amp hours. However,
From
I
which
only-
graph? Show me the graph.
Yes. This came from the lead acid data sheet. Temperature effects in relation to battery capacity.
Well, if I looked at your reference sheet, by the way, I wouldn't know that. You didn't reference, again, you suggested IEEE as a method of referencing, okay? Which none of your references were, but I just want to blow that by you, okay? So these cryptic links from Amazon or whatever don't mean anything, they change from the other day, okay? Anyway, keep going.
Yeah, so since from the data sheet of the lead acid battery, it doesn't really specify the curve on what the curve will look like if I discharge it by using a 1 amp load. So because for this one, it's discharging it for 1 hour. This one is for the 4 hours, and this is for the 10 hours. So I just took the average of these two graphs, so it is somewhere in between, and I just followed this graph here.
Okay, I don't know. So that graph comes from your manufacturer?
Yes.
Okay. Okay, so it comes from the manufacturer, and you interpolated the values, that's fine, okay? But, and so you found that, I don't know, it was 0.17 of charge, okay? So then you said, if you divide that by the amount of current draw, which is C, you're gonna get X number of hours?
For these values you're talking?
Well, that's capacity right there,
Yes.
right? Okay, so if you have that, let's say you get the maximum capacity for that battery at 20 degrees Celsius, or whatever the value is there, so it should be what? Should be 85% of whatever that
Yeah.
0.17 is, okay? Right, so it's 5.1 amp hours. So how much time theoretically should it take you to discharge that battery?
For this condition
Yeah.
here, well, since I am using a 1 amp load under 20 degrees Celsius, so it should. So by using the discharge current that I have, dividing it by the maximum storage capacity, which in this case is 5.1 hours. So you should end up having about, well, you divide 5.1 divided by
Drop your
1
calculator, yeah. So you divide 5.1 by 1, and you get 5.1 divided by 1. It's not a trick question. 5.1 divided by 1.
1.1.
What? 5.1 divided by 1.
5.1 hours.
Okay. Now, go back to your other graphs there. Let's remember that number. Keep going down, get some better graphs than that there, the graphs where you define discharge capacity. Oh, that one wasn't done, I guess. If you look at that graph you had there,
This one?
yeah, it had time on it there, that's all I wanted. Okay, so you found time being 3.9, I think, hours and 3.12. So why did you not get values that were comparable to 5.1?
Oh, because I was still referring to its original capacity of 6 amp hours instead of the new maximum capacity. I was referring to its overall.
No, well, you have C theory, 5.1 amp hours.
Yeah.
Then you have C actual, 3.92 amp hours.
Yes, to get this should have been, this value is actually referring to the 6, what I had in my head was 6 amp hours, but I was just estimating how close my actual value is to the.
Well, that's what I'm asking, why is there a discrepancy between the two? And what I want to point out to you, or make you realize, is you weren't testing under the same conditions as what you were calculating. When you calculate 5.1 amp hours, and it takes 5.1 hours, what do you assume the battery condition at the end, as far as depth of discharge? What is the depth of discharge of your battery after 5.1 hours of a 5.1 amp hour battery discharging at 1 amp?
Well, discharging it at 5.1 amp hours, and if you discharge it by after 5.1 hours, that means your depth of discharge is 100%, which.
Now, let's look at actual. What is the depth of discharge of your actual battery when you finished your data capture?
Is it this one here?
No, what was the depth of discharge?
For the lead acid battery?
Doesn't matter. Which one?
Well, it depends on which type of battery, according
Well,
to
we were talking about the lead acid battery, so let's
Okay.
keep talking about.
The lead
What was
acid-
the depth of discharge of your lead acid battery when you decided it was going to be a 3.92 hour? How much depth of discharge was your battery at that point?
Well, regardless of the conditions here, I still discharge my battery, referring to the data sheet, and it's recommended.
All of its energy, the depth of discharge was 100%?
No. Well, assuming that the cutoff voltage is always 9.
Oh, okay, so
9.6.
cutoff voltage, okay, so this will stop at the cutoff voltage.
Yes, that.
Your theoretical calculation, what cutoff voltage did you use there?
I decided to go for 9.6 volts for the lead acid.
No, the theoretical value, when you calculated that one, what was the cutoff voltage there? When you took 5.1 amps divided by 1 amp and came up with 5.1 hours, what was the cutoff voltage you decided to observe there? Again, it's not a trick question here. Did you consider a cutoff voltage?
Yes, the approach that I
No,
did.
you took 5.1 amp hours divided by 1 amp, and you got a value of 5.1 hours. You didn't consider the cutoff voltage. You will always get a lot less than your theoretical because you're stopping the battery before its depth of discharge is 100%. Whereas in your C theory assumed a depth of discharge of 100%. So why did you stop it at 9 volts or whatever it was?
Well, the data sheet of the lead acid battery indicates that the cutoff voltage for this particular battery is 9.6 volts.
So what does that mean? What is the cutoff?
The cutoff voltage means that anything beyond the, anything under the cutoff voltage, which under 9.6 volts, could damage or ruin the battery. And if you keep doing this, it will reduce the maximum capacity of the battery. Even at rated temperature, maybe your overall capacity is only now at.
Could you have stopped prior to 9.6 hours? 9.6 volts? Could you have stopped above that?
Well, you could, but for me, in my case, I was trying to get as much storage capacity, just to test the battery, how much storage capacity it can provide from the depth of discharge of 0 until the cutoff voltage, whatever the depth of discharge is at that voltage
Okay,
level.
well, you should have stated those numbers then, okay? Because you're really kind of comparing apples and oranges, because the two batteries aren't experiencing the same amount of discharge at any given time. right? Because the other one was what, 10 volts, I think, or
For the lithium ion, yes.
lithium ion or whatever it was, right? Okay. Right. So you gotta be careful of that, okay? Your data is there, but it's gotta be comparable, right?
Yes.
Anybody else?
Go ahead.
You said one recommendation is you would use a thermocouple.
Yes.
What benefit would a thermocouple have?
Well, the thing is, one major factor for me, the error of my project must be I only estimated the time I should leave the battery in the freezer. Well, so ambient temperature, and you put the battery in the freezer to let it cool. I don't have the exact time of how long it'll take before it reaches the temperature equilibrium. You could by using a thermocouple, you can estimate the time of how long it'll actually take, and considering
What would you be measuring as opposed to the ambient air?
the internal, maybe if you just the temperature of the battery alone.
That's where some of your data is a little
Yes,
faulty,
that
because
could be.
what did you say happens when you start drawing current from a battery? What happens to the battery?
It heats up.
It heats up, and your method of measuring doesn't take that into account, right? The other thing that I would point out too is more likely, I don't know what kind of freezer you're using there, but most of those freezers, you know, they have trip points that
Yes.
are 5-10 degrees apart there.
Yeah.
So, you know, at any given point, it may be higher or lower. It may be averaged at that value, but it's not. Right? So you could use a thermocouple or a temperature sensor.
Yes.
You had a DAC there. You could hook up the DAC. You could monitor your temperature to the minute, to the second, to whatever you wanted.
Also, maybe another error factor is that even if I leave the battery in the freezer, it is discharging in the freezer, and I cannot guarantee that the temperature is constant at that temperature. Let's say it's set at -15, it could still fluctuate.
Oh, that's what I was saying. So you could have tracked that all with the DAC. And
Yeah, that's right.
Kind of were both batteries, was the lead acid battery a deep cycle battery?
It is
It is?
a deep
So
cycle, yes.
it's marked on the spec sheet as that. And I guess my second question there also that goes with that is, if you couldn't get the data off the lithium ion battery for the graphs and that, why didn't you go find one that did have that? You're in charge of your experimentation, right? So you should have said, well, if these guys don't want to supply me with the data, I should go elsewhere, get something else.
Yeah, but the problem with that is maybe not all depending on the manufacturer, it could be different. So if I refer to this particular lithium ion, which may not be the same.
No, go buy yourself a battery that has the data available. That's what I'm saying. You bought the battery,
Yeah.
you selected it, and they didn't have the data available for you. So why don't you just say, well, I'm not going to pick that battery because I need this data, so go buy another battery. Right?
That's right.
Because you didn't have any expected data for the lithium ion to compare to either, so you don't really know if they're
Yeah.
in theory similar anyway, right?
Yeah, so for the lithium, I was just comparing it to its actual maximum capacity.
Well,
of 6
not,
amp.
yeah, it's what you measured, right?
Yeah.
Exactly. Anybody else?
2 more minutes if you have more questions. Okay. Good, good. Thank you.
Oh, before you go there, I just want to make sure I have everybody for this morning's attendance there. If your name's called, answer please. Jay? Here. Mateus?
Here.
Louis?
Here.
The other Louis?
Yes.
Nathan? Justin?
Here.
Arpit?
Here.
Yeah. Yes, sir. Juan?
Here.
Jake? Nissan? Okay, everybody. Thank you. The rest of you I saw. Yeah, I'm only spot checking certain people. No, the rest of you I saw a while ago. There was some that I didn't see and I didn't just want to make sure. Yeah, no, but I saw you a while ago. No, it was people I didn't see that I. I saw you all ago, okay? People I didn't know I saw. It's just, there's certain people I didn't see, I just didn't want to remind them that. And then the presentation starts, I ran over here. Oh, I didn't get anything for that either. You did? Yeah, well, I know that's what I talked about.
Everything has a solution. Everything has a solution, just hope. Yeah. Where are you going? Washroom? I'll wait for you outside. See you right here. Yeah.
Yeah, if I didn't get you, I had you.
During break. I missed a few people. Yeah. Yeah, you're good.
All right, I can go eat. There's 2 more this afternoon?
2, yeah. 2 this afternoon, yeah. Jake and Louis.
Louis, which one?
Louis Bonifacio. Did I say that right? Bonifacio? Is it?
His demo is in the lab.
I don't know how we're gonna do that for the screen. I thought about it.
With the what?
The screen.
Oh, just.
Remote demonstrations. I mean, we could probably do it from this, but I have to probably stop streaming here and then.
We can just say something.
How many of you
Yeah.
these are missing?
We'll save it for after the question period. We'll go after.
Yeah.
That seems to work a lot better though, the whole presentation with the camera and.
All I did was just fix this thing so that it just stays and gives this, right?
That's the way to do it.
And the only other thing we could do better for next time would be to, in the CSR, put a specification for slides such that, like, I mean, I could easily move
I
this
see
over
what
here.
you
Like,
mean.
for most people, it seems like this should have been over here.
Yeah.
But if we put a specification in the slide that these 200 by 300 pixels are reserved
Yeah.
and not to use it
Yeah.
for anything
In
else.
fact, to put it in their template, maybe a blue screen or something.
Yeah, right? Yeah. Well, no, because
Or
then,
not,
it,
no,
'cause
what-
then it would show up
Oh,
here.
that's right, that's right.
Yeah.
Yeah.
Yeah. So, but just to not use that section. See, I gotta go to my car and get my lunch actually.
Oh, I gotta go. Actually, I got some students probably waiting for me, so I'm gonna go.
Yeah,
over.
I'll see you after.
Yeah.
Yeah.
Are we locking this?
We can.
Probably should, eh? So
Yeah,
you
we
wanna
can.
lock the back, and I'll lock this one.
Yeah, okay, we can do that.
Do we have the keys for that?
Oh yeah. I just
It's
thought
just our key.
we probably should, well, they'll find out after this lunch hour and just see that there's some stuff in here.
Oh, that's even more reason I want to close this down then.
Well, yeah, like there's somebody's tablet there and there's a, so yeah, we'll lock it, but maybe we should announce to people we are gonna do that.
Okay.
But I'm gonna,
Well, they can always run and get the security guard and lock it.
but also, I guess they're gonna find out after today that it's gonna be locked, so.
Let's
yeah.
learn.
I just thought if they need the stuff, well, yeah, anyway, yeah, we'll lock it.
Not sure. When I got here, it was already open, so.
Oh, so they already put it onto your.
I can't believe after all these couple of years since they renovated, it still smells like cat urine.
Yeah, I was. Why does it smell like that?
It's because of the adhesive they used for the floors. That's what we were told, anyways. It's just gassing out. It was really bad when we first.
Yeah.
Yeah.
When I walked in,
It really
like,
has
it does
a weird
smell
smell.
like cat pee.
Very earthy.
Yes, there's an address. It's all already open. They're all pretty
Yep, do whatever you want.
projector. That. What? The focus of the projector is.
Don't even play with it, man.
Man,
What did you?
been chilling.
Yes, sir.
Sao? Chỉnh cam nữa nè. Chỉnh thiếu điện tí nữa để chỉnh. Sao show cái này? Sao show này? Thầy giờ mình đặt cái đó lên đó, mình show cách. Đúng không? Đặt này này.
Oh, it sounds like a free man. I'm over here. This is the cool section. See the water. I see. Oh, that keyboard stand, I like that. Is it? No, it is. No, it says keyboard stand.
Is it a keyboard or just whatever? It's a whatever.
But this is here. I don't want to know what's he down. But I don't get forward.
I think they picked it was a public, one that I started in public so they probably saw it. Anyway, just my own personal channel. We should probably create one for the rest of y'all. Yeah, I never got around to it. We lied about one.
That's probably
What? So you want to go on this group like Joe's mind?
Yes.
And how doing this like clear the way, like we know strategy, what to say. I feel like
Let me get there.
Yeah, that's the rate. Still walking. C'est beaucoup de ça. One day he decided to, possibly.
I have a lot of time to say no.
Okay, so starting us off this afternoon is Mr. Jake Wynn with his battery charge controller.
Yes.
Go for it.
Good afternoon, everyone. My name is Jake, and I'm a student of electrical engineering technology, and I chose the path alternate energy system. And today I'm going to talk about my project, the project that I have been working for 6 months. It's about the battery charge controller. Right. So today we're going to go over these content. It's going to be the purpose of the project, the functional overview, the schematic drawing, the test result, conclusion, and the background, and the reference. Right. So we're going to talk about the history of the battery charge controller. The battery charge controller, also called as the solar charge controller, and as its name, it plays a vital role in solar system design. So take a look at this diagram. So you can see that in this diagram, there's a charge controller connecting to the solar panel and the battery bank and the inverter. So my project is about the controller. So this project is contribute for the solar energy design system. So the purpose that I made for the charge controller, and the charge controller can protect the battery from overcharging, like for during the whole day, like 12 hours days, the sun will light up the solar panel for a long time, and without the charge controller, the battery will be overcharged and it will be damaged. So the purpose of the charge control is to protect from overcharging. The second purpose of this project is about it can regulate the power flow. Well, without a charge controller, the battery will be charged with excessively large amount of power, like around more than 1 amp, 50 watts. So the charge controller will limit the power flow that is fitting to the battery. The last purpose of the controller is preventing the reverse current flow. So we talk about the days that it will protect the overcharging, but for the night, when the solar panel is inactive and there will be no power supply, so without the controller, the battery will be discharging back to the solar panel and it will damage the solar panel. So the charge controller will protect the solar panel and maintain the capacity of the battery. And so that's a brief history of the charge controller. So moving on, we're going to talk about the functional overview. This diagram, you can see that on block 2B, we have 9-volt power supply. My project is designed to use a 9-volt solar panel. So I use power supply and set it to 9 volt as a simulation of a solar panel. So the power supply will supply for 3 main functions. It's the power source indication, the voltage regulation, and a reference voltage adjustment. The voltage regulation will supply the output voltage to the differential amplification, and so does the reference voltage adjustment. The differential amplification is an important function of the charge controller. It receives 2 signal input from the regulation and the reference voltage, and depends on the output, the input of those 2 functions. It will produce an output voltage to control a MOSFET switch, and the switch will, based on the the voltage, the signal from the amplification to maintain and regulate the current feeding to the battery. For the power source indication, I use a red LED to indicate that the solar panel is active and the battery is being charged. At the battery will send a signal to a voltage comparison, and at this block, the voltage will be compared to a reference voltage and then it will send a signal to indicate the battery reached 75% or battery reached 90%. For the 75% indication, I use a yellow LED to indicate that the battery has 75%, and so does the 90% indication. I use the green LED to indicate that the battery has reached 90%, and especially when the battery reaches 90%, it sends a signal to a function block called charging disconnection. It will, at this block, I use a relay coil anomaly close to disconnect the charge process immediately. Right. Moving on to the concept drawing, I would like to describe my project a bit. In the front view, there are 3 LED indicating the status of the battery and the status of my project, and there are 2 connectors indicating the output for connecting to the rechargeable battery, and the length of the enclosure is 38 centimeters. On the side view, we have 2 connectors for power supply for connecting the solar panel, and the width of the enclosure is 23 centimeters, including the length of the connectors, and the height of the enclosure is 10 centimeters. And from the top view, I use a glass cover plastic so we can see the PCB and the component inside. So moving on will be how the circuit works, will be the schematic drawings. So at this drawing, I'm gonna divide into 2 main schematic drawings. The first, I would say, it's about the charging regulation. For the charging regulation, we start on the power supply. The power supply will supply the voltage regulator that I use the LM317, and the LM317 is a special component that can set a desired voltage using 2 resistors R3 and R4 to set a constant voltage that is feeding to the first input of Q1, the transistor to N3904. And on the very right hand side, I use a potentiometer as a reference voltage, and this reference voltage receives a signal from the battery that the battery is sending a feedback voltage to the potentiometer, and this component will act as a voltage divider and send a signal or reference voltage to a second transistor Q3, second input. So the Q1 and Q3 I use 2 transistors, and it's a differential amplification. This is a important function an important function because for this component, because it will compare and amplify the difference voltage between the input of Q1 and the input of Q3. So if the input of Q1 is smaller than Q3, then the output of Q1 at the collector bin will become higher and higher, and this input will be sending to the gate pin of the MOSFET Q4 I use a MOSFET NDP602p as a switch to maintain and regulating the current going through the MOSFET and feeding to the battery. So this is also an important component for the charge controller, because take a look at this graph. As we can see that the gate to source voltage depends on the gate to source voltage. It will control and regulate the current going through the switch and feeding to the battery. So the higher gate to source voltage, the more current conduct through the switch. So back from the schematic, we can see that if the battery will send the signal back to the potentiometer, the potentiometer will send a signal to Q3. So it means the more voltage battery have, the higher voltage Q3 that receive, and if Q3 receive a higher more voltage, then Q1 will produce a higher voltage to the gate pin of the MOSFET, the pin 1. And we know that the pin 3, the source pin of the MOSFET, has a constant voltage, 9 volts. So it's based on this graph, we can see like the gate remain the same. However, the source remain the same, but the gate is keep increasing. So it means the gate to source is decreasing. So as gate to source voltage decreasing, the less current will go through the switch, and less current will go through the battery. So in shortly, the more voltage battery has, the less current that is feeding to the battery. So that is the first phase of the schematic as the circuit, the regulating part. The second part is the charging indications. At this part, I use 2 voltage comparator. I use LM311 as a comparator to measure a battery voltage, that is battery voltage and the reference voltage. The comparator will measure and compare those two batteries, and depends on the signals. If the negative terminal, the negative input of the comparator is higher than the positive of the input, and based on this simplified schematic of the comparator, the current will go through from the source, go through the yellow LED and turning it on, and go through the pin 1, the emit out. So it means that if the voltage of the battery is higher than a reference voltage that I set, the yellow LED will be turning on, and it will indicate that the battery has 75 of its capacity. Same as for U3, I again use an LM311 and measure and compare the voltage between the battery and the reference voltage. At U3, I set a higher reference voltage by using a voltage divider terminology. 2 resistor or 16 and or 15 set a reference voltage for the input, positive input. And at the output at pin 7, I can use a green LED to indicate that the battery has reached like 90%, and when the voltage of the battery is higher than the reference voltage, there will be a current going through the green LED, turning it on, indicating that the battery has 90% of the capacity. However, I add a relay coil anomaly close to energize, and when the coil is not energized, the switch, the internal switch will remain closed, keep charging the battery. However, if it's energized, the current, this internal switch will open and it will stop charging immediately. So that is how my project function through the schematic. So after building the enclosure and building the PCB board, and then I conduct 2 tests. The first test I want to test is the reverse current protection. To conduct this test, after I connect the power supply, connecting and charge the battery, and then I turn off my power supply, and I just did it for 30 minutes to see if there's a current go back to the charge controller. I use a multimeter to measure the reverse current, and for 30 minutes I measured like there was no current go back through the charge controller, and all components within the charge controller remains in a good condition. So from this test result, the charge controller has successfully protected the battery and the solar panel from reverse current. And the second test that I carry out is the power limitation, and I just charge the battery for 5 minutes, and from this table we can see that the output voltage, the battery voltage level is slowly increasing while the charging current is rapidly decreasing, and from the power is a small amount of power is feeding to the battery, so it means that the charge controller has successfully regulating and remain a safe power charging to the battery, so the battery will be damaged or explode. However, after making the project, and I would like to, this improvement that I could have done is make a better enclosure choice. My enclosure is quite bigger, and there are a lot of unnecessary space, so I would like to choose a better and smaller scale of the enclosure. And my PCB board is quite bigger, and as it's bigger, there will be a lot of power loss through the track and some loss. And the third improvement that is I would like to make the test longer, through the whole day or through the whole night to test the charging. So because of the safety issues, so I cannot make the test longer. In conclusion, the battery charge controller contributes to the green energy usage. As we know that the charge controller plays an important role that is in the solar system design. So it means that the charge controller contribute for us to use the solar energy, green energy usage. And nowadays we move on, we use more and more solar energy as our green energy. And from the test overview, I would like to say that my project has protected the solar panel and the battery from overcharging and discharging, and the regulating the power flow of to the battery. And in future use, I would like to, I hope that my project will be utilized for, could be smaller scale for electronics with a smaller size of solar panel, or my project can be used for bigger scale for industry. And I would like to say special thanks to Mr. Juha as my advisor to lead me to this successful day with a successful project charge controller. And these are the reference that if you would like to get to know more about this information, you can visit this website and books. So that is everything for my presentation. Right now I will demonstrate how my charge controller works. Right now, as you can see that the battery charge controller is regulating a small amount of current that is fitting to the battery. So my charge controller is reducing the current that is fit to the battery. So as the battery is being charged, the next current will be decreasing and maintaining a safe charging current if the battery is almost full. So secondly, I would like to test the reverse current flow. So right now I will turn off the power supply and see that if there are any reverse current going back to the charge controller. Power supply is off, and when I turn off the power supply, there's no any reverse current going back to the charge controller. So in conclusion, the charge controller has successfully protected the solar panel from battery discharging. So that's my demonstration, and that's everything for my presentation.
Can you just maybe there's a battery in that box?
Like
in your device, there's a battery there. I'm just not seeing it.
No, there's no.
So how can you say that the device was regulating the battery as it was charging?
Because the
Oh, it's right there. Sorry, I didn't see the battery. That's why.
It's
I was looking for a battery. Couldn't see a battery. So.
Yeah.
So, what does regulating mean?
It means controlling and the save current charge to the battery.
So is it a current regulator or a voltage regulator?
Current regulator.
Current regulator, okay. And your triplet meter is showing us what?
Right now it's showing if we can see the reverse current, I turn off the power supply. And
So it's an ammeter?
Yeah, it's an ammeter.
And you bring back the schematic, where is it measuring on the schematic? So where on your schematic is it measuring?
I use the multimeter to measure and
Yes, so where does it measure the current?
I just use a multimeter to test it right now.
I understand that. Where are you testing? Current has to be tested at a location, right? Where is it testing at?
It will be testing between the output and in series with the output of the charge controller and the battery.
Okay, so where will that be there?
It will be at the positive of the charge controller.
So the way it's set up, then you always need an ammeter in your circuit?
No, because
No.
I just want to test and
Okay.
see if there's current.
One just quick question. I noticed on this schematic, and if you go to your other schematic, your terminal locks there, you put them in backwards. Like, you have wires coming into the terminal lock this way, but you connect things to the outside, and you have arrows showing. That J1 should be facing the other way, and J2 should be facing the other way. Right? Anybody else?
Well, while we're on this slide, is there a particular reason R2 is positioned where it is?
At first it was I placed a yellow LED, but it was to indicate the battery, but I realized it was a wrong indication, so I moved the yellow LED.
Okay. It's just a little misleading because it almost seems like it's connected to the power supply, but it's not. It's a Q2 at the top.
Yeah, it should definitely be closer to Q2.
Yeah.
So can you tell me a little bit, since you have this slide, can you tell me a little bit about how does your differential amplifier there work?
The different amplification works like it will receive two input signal from the battery and from the voltage regulator. I set a constant voltage regulator, a constant voltage output of the regulator for 3 volts, and if the output of the input of Q1 is lower than Q3, the output of Q1 at the collector will be higher than the output of Q3. So it means like input of Q1 is lower, and if Q3 is higher, then the output will be in the opposite. So it means if the battery has more voltage, the Q1 will produce larger voltage, high voltage, feeding to the gate pin of the MOSFET.
So what happens with the MOSFET?
The MOSFET, according to this graph, we can see that the gate, the source is connected to the power supply, so it will remain constant 9 volts. However, the gate is increasing, so it means the difference between the gate and the source voltage will be decreasing and decreasing, so the less current will go through the MOSFET.
So go back to the slide. So explain to me once more, how does the differential amplifier control the MOSFET?
once Q1 and Q3 receive two input, the Q3 receive a signal from the battery, so that the Q3 has more voltage. The voltage of the input voltage of Q3 is increasing, while the input voltage of Q1 is remain the same, constant. So the output of Q1 will higher as the input of Q3 is higher. So if the output of Q1 is higher, the
No. So Q3 has a high voltage. Let's go one step there. So Q3 has a higher voltage because the battery has a higher voltage. Okay.
yes,
Q1 doesn't change. Okay. So what happens then?
it means it will amplify the difference voltage between Q3 and Q1, and the higher voltage will be produced at the collector side of collector pin of Q1.
Okay. So what voltage range are we talking about there? How much? Millivolts? Volts?
Volts, around 7 to 8 volts,
Okay.
could be reached 9 volts.
Okay. 9 volts. Okay. And then if you go to your next graph, where's the 9 volts in all of this?
This is the gate to source voltage, so it's like the difference between gate to source.
Okay, so how much would that be if the voltage is 9 volts on the output of Q1?
If the gate will be 9 volts and the source is 9 volts, so the gate to source will be around 0, and the current going through the
Okay, well, if it's 0, we're not seeing,
it's,
on your, pick a value that's on your graph at least.
at 0 amps.
So that means it's going to get cut off. So you have a battery that is higher, so therefore less current going through. So it's not going to charge as much. Okay. And then what you're hoping is eventually it catches up on the PD side. Is that what you're saying?
Yes.
All right. Anybody else? Bring up where your comparators are. Can you tell me what pin 2 and pin 3 are called on U3?
U3 pin 2 is called the input, positive input, and the pin 3 is the negative input.
You're sure? Yeah, that's what you saw on the spec sheet?
The spec sheet.
You saw it called that in your spec sheet?
From that small second picture.
No, but in the spec sheet, that's what they call that? The negative input and the positive input in your textbooks? They call it the positive input and the negative input?
It's marked with a plus and a minus symbol, but what's it actually called? That's the question.
I haven't read that part yet.
You didn't read that part? Oh my God, did you take it?
There's your assignment for tonight.
Yeah.
Yeah,
It's not called positive or negative, okay? Look it up.
look it up. I had a question about this relay.
Yeah.
In the data sheet for that relay, did you notice, is there anything to protect against the freewheeling effect? The electromagnetic release of that coil?
I use a small scale of the really not this small.
Yeah, well, I don't care how small it is. What's the property of that relay coil? What does it possess? What's the property of the relay coil?
It has an inductance.
It has inductance, right?
Yes.
So when this relay coil gets switched on and off, okay, so let's say that there's, what's the current in that coil? Do you know what the nominal current is? The nominal coil current? Huh?
I haven't read that.
You don't know what it is? How do you know that, how did you know how to design the circuit properly if you didn't understand what the coil current is? There's a few questions I have here. So, what's the voltage? Let's go that way. Do you know what the voltage is for that coil? What's the required voltage to activate the coil?
I have no answer.
You don't know anything about this relay coil that you put in your circuit?
Is it in the circuit lamp?
No, it's not.
Why not? Why is your
Because I have
documentation
some wrong trace in PCB designs.
So why isn't your documentation updated for that then? Or at least indicate that that's not the current documentation for.
I'm kind of curious here, like, what's the relationship between the power supply, the green LED, LED3, and the coil?
When did the green LED supposed to come on? When did it come on there a while ago?
When if the battery voltage is higher than the
When you did the demonstration, when did the yellow LED and the green LED, you get LEDs there, I didn't see them come on.
because I have an issue with PCB designs on it.
For both the yellow and the green LEDs?
Yes. So wrong schematic for PCB.
So this is really fictitious.
So you based your PCB design off of incorrect schematic?
I just made a wrong PCB, but the schematic was
How could you, what kind of software did you use to design your PCB?
KeyCAD.
And so how come, if the schematic reflected what's here, how come your PCB design would get error if you followed the workflow of the software?
I didn't realize until like this last Friday,
Didn't realize what?
the wrong trace for my,
But if you did the workflow properly in KeyCAD, doing ECRs and DCRs and looking over your work and that, before it ever got approved for manufacture. Because these are all, if this doesn't match your PCB, this is on you, not on the PCB manufacturer or anybody else, okay? So why did you go through the workflow of that and in the ECR and the DCRs correct the faults that was probably there? Did you run a DCR,
Yes.
design correction rule check? And were there warnings and errors?
no.
There were no warnings and errors, yet the schematic and the PCB didn't work. We better call it KeyCAD. There's something wrong with the software then. We better call KeyCAD.
I say I made a wrong connection on the PCB, so like,
No, but if you took a software that had the schematic, KeyCAD, and you could use that to design your PCB, how could you have wrong PCB layouts?
I made a mistake in running with the trace and connect the wrong location, so it resulted in a wrong
So you didn't use the
schematic.
tool properly. That's what it is.
Where did the mistake come from? Did the mistake come from the schematic? Is the schematic wrong?
No, just like during when I draw in a PCB
How did your initial piece prototype work?
from the schematic.
Did it work?
Yes, it was.
Exactly like it was supposed to work?
Was it based on this schematic?
Yes.
Okay. Yeah.
Yeah, can you go through your testing? Second test. Yeah. So here you're saying power limitation. Now these are your test results. So what's the conclusion here?
The conclusion is the charge controller is successfully limiting the current and delivered the same power to the battery.
How do you know what the battery wanted from home?
So it's limited for 5 watts?
Yes, less than 10 watts.
And you getting this results against what? What's your reference? You basing that on your component? Like, I see there's some measurements there, and you're saying this is 5 watts. So you're saying the limitation is, so I can't have that charge controller to work if I want to charge a battery of, I want to charge 10 watt? Doesn't work?
It doesn't work.
Why?
Because the charge controller will limit the current with less than 1 amps.
Will limit. What component will limit that?
The MOSFET will limit that. The MOSFET, conventional meter, and the differential amplification will limit the
Oh,
current.
so you said to limit that.
So the MOSFET, it limits what, the current, right?
Yes.
So when you were charging your battery, did you limit your source to 1 amp? The power source? I mean, the power source, did you limit it to 1 amp, or did you try to go 2 amps and you still get it to that point? That's my question. Have you tried like using a power supply, you set the power supply to provide 2 amps and you still get this result?
Yeah, I still get that result. It will rapidly.
Oh, you did that?
Yes.
Okay. Thank you.
You're welcome.
Can you read out your block diagram? We got a few questions here. The MOSFET switch is a 3-terminal device, right?
Yes, 3
So this 3-terminal device, so it has a signal coming in to control it, has a signal that is controlling or that is coming into it, and there's a signal that is controlling. How come your box there is a 2-terminal box then?
This thing like the differential amplification, I guess like a significant signal to control MOSFET.
Okay, so that's the controlling, and I'm assuming what's coming out of it is the controlled signal. Where's the input signal? The brute input signal. The uncontrolled signal.
It will be from the source.
Sure, so where's that from?
I did not put it in.
Charging disconnect. That's the same thing. So when your battery reaches 90% indication, your charging disconnect. What happens there? What does it do? It disconnects what?
It disconnects it will open a switch internal the relay coil will disconnect like a connection between the charge controller and the battery.
So where is that? Where do I see that? Your block just says charging disconnect, but shouldn't that be in series with the battery somewhere? There's fundamental flaws in your layout here, like, and I think that's hurting you when you go to try to understand your actual circuit there. What's yeah, well,
1 more minute.
one test that I would like to see is maybe efficiency. How efficient, how much of the energy is being dumped versus being passed through battery. That is best performance. Okay, good.
Yeah, that's what I'm feeling.
It's all these huge boundaries, going to the small. It's rivers, just rivers and she was always flashing. See, I don't like the trees and all these things. You're not for 2 weeks. We're supposed to take every night. After that night, we stay on the hill and all the
Well, I just happened to be looking at the book here. Well, no, what do you want to do? It's your demonstration. You want to, what did he work it out with you? If you want to, use a video, you can do it. But if you want to go demonstrate why,
I don't know how
so you're still going to do the demonstration in E211, right?
Well,
that's what you're planning on?
okay. That's what we have planned.
He says he's not walking over there because So you better be sure what you're doing. And I'm about to introduce you, so.
Yeah.
So you're gonna do the demo down there? Okay, so next up we have Mark Louis Bonifacio and his Pico Hydro Performance Analysis. And just to let you know, after this presentation is over and we have the question period, we will be going to E1011 to view a live demonstration. Take it away.
Thank you, Mr. Rod. Good afternoon, everyone. I'm Louis Bonifacio and I'm taking EET, Alternate Energy Option. So today I'm going to present the senior project, which is about the Pico Hydro Performance Analysis. My advisor for this project is Mr. Sula. So just a quick overview of what I'm going to discuss for my presentation. I will talk about introduction, purpose of the project, overview of the Pico Hydro system, block diagram, some technical information like the concept, design considerations, project build, wiring for analysis, testing and analysis, conclusion, and recommendations. So when I was thinking for a project for my SPL, I decided to do something that is more related to the field that I'm taking right now, which is alternative energy option. So when the topic of discussion is about renewable energy sources, usually the first things that come to our mind are solar, wind, geothermal. But undoubtedly, these energy sources have gained popularity over the years, and especially for small-scale applications too. However, these are not the only energy options that we can utilize as we move toward a more sustainable future. Hydroelectricity can also be a viable and realistic option. So, on a personal note, way back in my home country, our house is situated near a hydroelectric dam, and it fascinates me how such a system can supply potable water and generate electricity for the entire province. So, because of that interest, I decided to do something related to hydroelectricity, and I also take this opportunity to learn more about the system. As we all know, hydroelectricity is the technology of harnessing energy from moving or flowing water and convert that to electrical energy. So this is the basic energy transformation. Potential energy from water is being converted to kinetic energy, and that kinetic energy turns the turbine, and that mechanical energy is being converted into electrical energy. So equation 1 is the general formula for hydropower system. I believe most of us are familiar with this formula because we have encountered this in our introduction to power system course with Mr. Broad. So the turbine output power is directly proportional to the volumetric flow rate of water passing through the turbine and to the effective water head. So, over the years, the technology surrounding hydro system have also evolved, and from producing hundreds of megawatts, it can also now produce a few hundred watts to up to a few kilowatts. So for such small-scale applications, the system is called Pico Hydro, and it can generate less than 5,000 watts, and they are suitable for low-head applications, which is about less than 30 meters. The picture shown here is a basic diagram of a small-scale hydropower system. So this is a bit drawing that I did. Imagine this is a river flowing from high elevation. So a portion of that water is being directed to the turbine, via the water intake and the pen stack. And that turbine is used to drive, that water is used to drive the jet. Oh, sorry, that water is used to drive the turbine. And the effective head is actually the vertical drop between the water intake and the outlet of the pen stack. So the higher your head is, the higher power your system can generate. And also, the system can use different types of turbines. One is reaction turbine and one is impulse turbine. So the main difference between the two is that reaction turbine uses pressure of water to drive the turbine wheel, whereas an impulse turbine uses the velocity of the water jet to drive the turbine wheel. For pico-hydro system as well, we don't usually require a dam because it usually runs off the river, meaning to say there's no flooding and it's more environmentally friendly as well. But however, because we are utilizing river for our power generating source, the volume of water flowing through these natural sources tends to vary all year round. Meaning to say, there are seasonal variations in the amount of volume of water that that body of water can produce. So by installing a nozzle at the end of the pen stack, it can regulate the flow rate of water and therefore can compensate for the power variation. Which leads me to the main purpose of my analysis project. So it aims to understand the effect of nozzle diameter in the energy performance of a pico-hydro system. And aside from that, it also aims to determine the viability of the project in low head and low flow rate conditions. So, because access to naturally flowing water is very challenging for me, the system used a test assembly, which is for simulating the application of pico-hydro system. And yeah, as I said, there are some project design considerations that are incorporated to building that test assembly. First, it uses a Pelton turbine which is supplied by NBCC. I have a picture here of a Pelton turbine. So this is a Pelton turbine. It actually works on the principle of velocity, so it converts the velocity of the water jet, and that it uses to turn the turbine. And actually this one is from the previous similar project, from previous student. And it was actually in the lab, but when I did my initial testing, the pipe burst, and Mr. Ligier was there as well, so he witnessed how I caused flooding in the solar lab. So I had no choice but to rebuild the system, do another piping, and input some design considerations to it as well. So the basic component of a Pelton turbine is comprised of a Pelton wheel, which is composed of the runner and buckets, and the nozzle. So, another design consideration that I incorporated was to test the project on lowest possible water head, which is, according to the US Department of Energy, the lowest possible water head for a small-scale hydropower is about 2 feet or 0.6 meters. So anything lower than that, your pico-hydro or your micro-hydro will not be feasible. Aside from it, I also use a pump to circulate the water through the systems, which is, the pump capacity is about 4.6 liters per second. It is fairly low compared to, for example, the Peticodiac River has an average daily flow of about 63 liters per second, while Canaan River has about 147 liters per second as well. So this is fairly low. So I'm trying to test whether the system can work for such conditions as well. And then lastly, I want to minimize the pipe losses in the system. So I designed the system using shortest possible length of pipe and the biggest diameter that I can use. Now let's go to the block diagram of the project. It's actually divided into three main parts. First is the test assembly, which is the actual physical build for my test. And there's data capturing process and analysis as well. So let's talk about the test assembly. There's a water reservoir there which contains the water that's being circulated to the system. A circulation pump that draws 115 volts AC source to circulate the water. And there's a pen stop which is made up of 2 inches PVC pipe. And then at the end of the pen stop is the nozzle and the turbine, Moncton turbine with internal rectifier. So the water is circulated in closed loop. And as for the parameters that I want to measure, I wanted to measure the volumetric flow rate of the water exiting the jet nozzle. I wanted to measure the speed of the turbine as well, and the power generated when it's connected to a load. So this is the concept drawing for my project. So as I said, the water reservoir houses the pump, and it also provides the support for the turbine. And the pipe that I use is a 2-inch PVC pipe because the inlet of the Moncton turbine housing is designed for 2-inch. And yeah, there are 2 nozzles that are fitted in the turbine, but for this project I'm only using the one nozzle at the lower portion of the casing. And then the generator output is connected to a test panel for me to be able to measure the power delivered to the load. Okay, as for the wiring diagram, it's fairly straightforward. The Moncton turbine is a 3-phase permanent magnet generator, and it has an internal AC to DC rectifier. So the output of the generator is connected to a terminal block. And I have a test panel which have DC ammeter and DC voltmeter, and they are connected to a load to measure current and voltage. So this is the finished build of my project. As Mr. Bog said, it's in the solar lab because it's quite big and it's heavy because of the water intake tank. So I'm not able to bring it here. And there are 2 pipe coupling there. One on the left is for me to be able to take out the pump if ever there's maintenance or I want to replace it. And the other one to the right is for me to be able to shift the nozzle away from the turbine so that I can do my flow rate measurement. And at the bottom part is the electrical test setup, so it's fairly straightforward. As for the nozzles, so I opted for 3D printed nozzles because when I checked the price of nozzles from the original supplier, which is Power Spout, it is very costly and the lead time is very long, so it might affect my analysis and my schedules as well. So this is the CAD model for the pipe, for the nozzle, and the sizes that I intended to measure is 5 mm, 8 mm, 11 mm, and 14 mm. Now during the EDR2, Mr. Broad suggested why not test the system without attaching any nozzle. So I thought that's a good idea, so I also added additional testing for the 42 mm nozzle. Okay, so I keep on mentioning about nozzles, but I think I need to briefly touch about how the nozzle works on the system. So actually the nozzle follows the principle of conservation of mass. So meaning to say, the mass flow rate at the inlet of the nozzle, which is point P1, is equal to the mass flow rate at the outlet of the nozzle, which is point P2. And using continuity equation, which is equation number 3, flow rate is equals to the cross-sectional area at point P1 times the velocity of the fluid at that point. And it should be also equal to the cross-sectional area of at point P2 times the velocity of fluid at point 2. So from this equation, we can conclude that if A2, which is the outlet of the nozzle, is smaller than A1, the velocity of fluid exiting the nozzle should be higher than the inlet velocity. Okay, so much so for physics and fluid mechanics. Now let's go to testing. So the first test that I conducted is volumetric flow rate. So as I mentioned, in order for me to do it, I need to shift the nozzle assembly away from the turbine and use a bucket method. So I run the pump for 5 seconds using a timer switch, and the amount of volume that I got is being measured by measuring scale. Now I want to address why I did not use sensor for this and that. Initially I thought that installing sensors at the outlet of the nozzle is very challenging, and what I really wanted to measure was the velocity or the volume of the water coming out of the nozzle. But then later on I realized that it follows the principle of conservation of mass. Having said that, I could have installed a flow meter in line with the nozzle assembly. But then again, the cost of a 2 inches, let's say 2 inches flow meter is very, 2 inches Hall effect sensor is very expensive as well. And using bucket method is fairly a good option because it's actually being used in real life application if you're going to measure the flow rate and for the system as well. So this is the timer switch that I use. I set it to 5 seconds. And this is the equation for getting the flow rate. It's just volume over time. And this is the results that I got as expected. The higher diameter nozzle produces the largest flow rate, which is about 3.17 meters per second. It's like a linear trend. So the second testing that I did is turbine speed. Now, for this I use a photo tachometer. So when I run the turbine, I use it to measure the RPM. And this is where things get a little bit more interesting. So initially I thought that based on equation 1, the higher the flow rate, the more power the system can generate, and power is symmetrical or proportional to the speed of the turbine. However, based on the test results, that seemed not to be the case. As we can see, the highest nozzle diameter, which is 42 mm, produces a lower speed of the turbine. And the peak RPM, which is 672, is produced by the 14 mm nozzle. So I was expecting a linear or somewhat linear trend line as well. But apparently, that's not the result that I got. So I cannot sleep for days because of, not because of SPL, but because of this result. So I did some research. And I found a possible explanation for this. And this is because of equation number 5, which is the water jet power. This equation measures the power of the water jet at the outlet of the nozzle. So as we can see, this is directly proportional to the flow rate of the fluid at the outlet of the nozzle times the velocity of the fluid at the outlet as well. So here's the graph. I did some calculations using continuity equation to get the velocity of the fluid for each nozzle diameter. So as we can see, the orange trend line is the velocity of the fluid with respect to the nozzle diameter, and the blue one is the jet power. So even though the 42 millimeters nozzle produced the highest flow rate, the velocity of the fluid is very low. And that translates to a lower jet power, which is used to turn the turbine. So for the 14 mm nozzle diameter, it produces a jet power of about 30.19 watts. And yeah, this equation number 6 is the turbine output power, which is the hydraulic power at the turbine shaft. So we just multiply it. We just multiply equation number 5 to the efficiency of the turbine, which is, according to some studies, it's about 90% efficient. And yeah, I just have some photos for you to show. This is the you can see the amount of water coming out of the nozzle for each nozzle diameter. And the 5 mm nozzle failed to cause rotational motion of the turbine because of the jet power. So now we discuss about the electrical performance. This is actually the voltage and the current produced at the generator output. As expected, based on the turbine RPM, we know that the induced voltage in rotating machine is directly proportional to the speed of the speed. So the peak nodal voltage I got is 40.50 volts DC, and that's for the 14 mm. And for the 42, it's just about 14.23. And as for the power, it follows the same trend line as well. So the peak power that I got is about 10 watts for 14 mm and about 2 watts for 42 mm. So, after all this testing, what can I conclude about my project? Well, in a pico-hydro system that particularly uses a Pelton turbine, higher flow rate does not exactly translates to higher power generation. There's a certain limit that there's a certain limit of nozzle that the Pelton turbine can use in order for it to perform in optimum performance. And that can be achieved by varying the nozzle diameter. Secondly, the project was able to generate around 40 volts DC or 10 watts. And that's under very low head conditions and very low flow rate conditions as well. So if the project uses different height and different pumping capacity of circulation pump, I might be able to generate higher power output. And similar to different renewable energy sources, the system's generating capacity is also dependent on geographical factors as well. So if ever we want to install it somewhere, we recommend to do some proper site planning and assessment too. Now as for the project cost, if NBCC has not supplied me the parts, it will cost me about 3,400. But because the turbine is about 3,000 and the pump is about 150, I only spent around $200 for this project. Future recommendations, well, first, in order for me to improve my data gathering process, I should have installed the flow meter and DAC. And probably we can utilize more nozzle diameters to get better comparison on different sizes. We can also use a spear nozzle, but apparently this is very expensive. And but this can produce varying nozzle sizes as well. And then probably increase effective water head. And we can also use different turbine like a turbo turbine and compare the results of both. And these are my references for this project. And this is the project. I have some videos if you want.
You're still gonna take us to E1011 though, right?
Yeah. Right. So that basically conclude my presentation, and thank you for listening.
Thank you for the presentation.
Thank you.
How did you choose the diameters
Of the nozzle?
of the nozzles? Why 5, 8, 11, 14 and not something else?
Okay, it's basically based on the specifications of the Moncton turbine. It says that it can work for a minimum of 5 mm nozzle diameter all the way to 25 mm. So in my project, I chose 5, 8, 11, and 14. I was hoping to see a substantial outcome for that one.
When you did your tests, can you just bring up the curves there for a second? There was one I just wanted to ask clarification for. There was one, yeah, okay, so generator average no load voltage. Okay, so what was the purpose of no load voltage? Because that doesn't necessarily equate to anything purposeful, right?
Yeah, that's a very good point.
I mean, what's more important than the no load voltage?
Well, it's just basically to get the relationship between the turbine speed and the induced voltage of the turbine without connecting any load to it.
Yeah. Okay. Compared to what other test is better? Yeah. Go to your next slide.
Turbine speed.
Yeah, well, turbine speed based on power, right? Power is really what we're talking about, right? You're delivering work, right?
Yeah, work.
So in the end, so in the end here, which nozzle size, if you look at all your testing, whatever, which nozzle size is the optimum value?
Well, based on the samples that I have, the 14 mm seem to be the most efficient, but I forgot to mention that according to my other research, for a Moncton turbine, there's this thing called jet ratio, which is the ratio of the wheel diameter over the diameter of the water jet. So that determines how efficient your turbine is. So if the ratio is around 11 to 16, that's where your maximum performance. So I did some calculations here. The diameter of the turbine is about 240 millimeters. So for a 14 mm, that would give me about 17 jet ratio. If I use about 20 or 24 mm diameters, I could probably be on the range of 11 to 16 jet ratio. Yeah.
Okay, so in other words, what you're saying is you're kind of outside of that window. Is that what you're saying?
Well, a little bit outside, but close to it.
Yeah.
Yeah. If I have used 16 or 20, I might be inside that range. Yeah.
That would have been an interesting graph to look at.
Exactly.
Maybe, like just where it falls, where your testing fell within that, and where your results fell.
Right.
Even just putting that as a background area here or something, right?
Right.
can you tell me the difference? You use the two terms pico and micro, and maybe I missed the start. Can you tell me the difference between the two?
Okay, it's just basically the classification of hydro turbine based on their output power, maximum output power. So for pico hydro, it can generate up to 5,000 watts. For a micro hydro, it can generate less than 10,000 watts of power. Yeah.
Okay, so in our case, much less.
Exactly, yeah. Initially, I named the project micro hydro, but since the capacity of the Pelton turbine is only up to 1.2 kilowatts, so I named it pico hydro, just to make it a little bit more appealing. Yeah.
Makes sense. One component was, again, maybe you didn't identify it, or what's the nozzle size that came originally with the device?
With the Pelton turbine? It's an 11 mm nozzle.
So it's pretty close to what you were calling optimum 2, right?
Right, yeah.
That would have been maybe something you could have added to, just to say, hey, by the way, you know, this thing originally comes with 11 millimeters, so, if you had found that 35 millimeters was the best result, then there were, are we doubting you, or are we doubting them? Because there might be a reason why they're not exactly at 14 meter, which is maybe a manufacturing process, or maybe it's just what they can get, you know?
Yeah, actually I checked the site, and we can actually order what size of nozzles do we want. So it depends on our energy requirement for site applications.
Yeah, well, that's interesting.
Yeah.
Be interesting to get one from them and at 14 and give it a whirl too, see if the outcomes are the same, eh? Yeah.
Probably. Or probably order another type of turbine, which is turbo turbine, that can work on low flow rate and low head conditions.
Well, this project opens up a lot of possibilities.
Right.
I don't know.
So for the graph, for the blue graph there,
Yes, sir. No, go.
for this one, yeah, this one will do, I think, right? It's the same thing. These are the nozzle diameter down there, right?
Yes, sir.
So you have 14, and then you go to 42, right?
Yep.
So in between, you don't have anything, right?
Exactly.
So in reality, this graph doesn't really reflect what we should expect, right?
Well,
because we don't know what we will have between 14 and 42.
Right. The only thing that I can conclude is that the maximum or the peak of the graph is between 14 mm and 42 mm.
I thought you had different nozzle sizes though.
I have, but that's 5, 11, 14.
There's a huge gap between 42 and 14.
My suggestion is you could add like a reference. You couldn't add a reference for us to understand, or did you find a reference of something similar to what you're trying to achieve?
You mean other
research?
There was, and actually it's kind of similar to it.
Like they had this, you could have brought that here. I mean,
just for comparison.
Yeah, just to prove my findings.
I mean, yeah.
That's it.
Well, I think he did well in the fact that he smoothed the curve.
Yeah.
He followed the trend. I mean, but they are right in saying that trend can actually dip way below, then come back up. You might be on the very end there. You might be on a rising.
Yeah.
You never know, right? There's no way of knowing what's happening between the 14 and. So I didn't realize.
True.
That.
Yeah.
Determine the actual.
He mentioned here, right?
You 3D printed them in the lab here?
No, outsource.
The outside. Oh.
You don't trust me?
Now, Mr. Ledger mentioned that the 3D printer might not be able to handle the water pressure, so it might leak.
Oh, yeah, he was afraid of another flood?
I did flood the solar lab for 3 times already.
So you use curve smoothing to find those those curves?
Yes.
What order did you use first? Well, not first, but second, third, fourth?
honestly don't have any idea.
Data like this, especially when you have big gaps like that, very often you would put down on the bottom there what the actual graph smoothing equation is, so that we would realize which order, and so again, looking into knowing, is there a tendency for that to want to dip slower or not? Because you're gonna linearize it too, right?
Yeah.
Maybe I missed it, but what is the actual size of the nozzle that was included with the unit?
It's 11 mm.
11 millimeters. Which is pretty much optimal then? Pretty close?
Pretty close, yeah.
Well, you got better, more power and more higher voltage with the 14, right?
Yep.
And the 11, did you use
more,
the
yeah.
stock one, or?
I did. It's lower than the 14 mm. But as Mr. Metcalf said, the maximum could be way after the 14 mm.
Yeah.
Yeah, especially on the power, for me, I tend to want to think that maybe it goes up for a while before it goes back down.
Yeah, right.
Does the manufacturer produce a 14 millimeter that you could order? Did you notice?
Yeah, they have, actually, they manufacture what do you call it? A nozzle that has not been cut, so it's up to the, up to us to order what's the size that we want.
So
they will cut it.
It's tapered and you cut it where you...
Yeah, that's the worst part.
Okay,
Yeah.
I see.
The gold nibble method.
Yeah.
Always going down and stuff.
Yeah.
How much was
Let's
that?
come back now.
Yeah.
How much was it?
For the nozzle?
Yeah.
Well, I checked and it cost me about $200 just to order.
So it is very expensive.
It is, because it's coming from Australia and they have to ship it here.
How much was it per nozzle for you, the printed one?
Well, it cost me about $20. Yeah.
For all of them, or?
No, for all of them, 4 of them is about 80, close to 80. Yeah.
And I think for what you were trying to accomplish, it's a fair trade-off.
Yeah.
Yeah. Yeah.
So why do you think the manufacturer provides an 11 millimeter nozzle and not a 14 millimeter? Is it, I don't know, is it worth the, there's a slight improvement there, right? In power?
Yeah. Well, that depends on site application, like flow rate and the head. Yeah. So I don't have any particular answer to the question. I'm sorry.
It's okay. Is there some kind of trade-off between jet power and velocity maybe, or, because the velocity is lower, right?
Yeah. So, as I said, higher flow rate does not really translates to higher jet power. So, the sweet spot is actually the combination of the two factors.
Of the two?
Yeah.
How about the head? If you change
Yeah, of course.
head, does it have an impact, or do you expect
I would
impact on the...
Yeah, I would expect an impact on that as well. Yeah. That's another future recommendations. Probably can be done.
In your introduction, you were saying good things about hydro energy.
Yeah, I'm saying it's viable and probably
Hydro, right? Is it bigger than BP?
Sorry, bigger than?
Yeah, the share of hydro. Do you think is it bigger than BP? In the worldwide generation, you did some history research there, right?
Well, I did some research in Canada, and it's actually the biggest power producing, what do you call that? Power producing plant. Yeah.
In Canada.
In Canada.
What about the rest of the world?
I haven't checked that.
Especially into the...
Norway and the Nordic...
the most...
Yeah, especially, or looking at, like in your case, low head pressure, micro pico. Those are markets that applications that have only come into play last, I don't know, 10, 20 30 years at best, right? Before that, whenever you talk about hydro, we think about all these large dams that a lot of countries, well, you can't do that, that's not possible, right? So this opens a lot of potential to that. And I think in the last, again, 30 years, I would definitely say there's been a lot of penetration in those markets for that kind of a solution, right? If I had a stream on my line, it'd be one of those, would come to it.
Yeah.
Thank you. Thank you.
Thank you. We'll proceed to E1011 for the demonstration.
Yeah, thank you for
Before we go there, just for an afternoon, 10 minutes. Johnny, Jim, Jed, here.